Hi, and welcome to this Microsoft Virtual Academy course on developing Microsoft SQL Server databases. My name's Graham Malcolm. I'm a senior content developer at Microsoft, and I'm responsible for the data platform content, both in the MVA and the classroom-based training that we deliver through our CPLS channel. Before I joined Microsoft, I was a consultant and a trainer and an author on various data platform technologies, particularly SQL Server. But I'm not the expert in the room today. I'm joined today by Christian Bolton. Christian, can I just ask you to tell us a little bit about yourself?
Thank you, Graham. You're very kind. My name is Christian Bolton. I work for a company called Coeo. We're based in the UK and we deliver consulting and managed services around the Microsoft data platform. I have a number of certifications, Microsoft Certified Architect Master and an MCT. I also spent 6 years as a SQL Server MVP, and I've written a number of books around internals of SQL Server and troubleshooting.
Fantastic, thank you. So it sounds like we're in good hands. What are we going to do today? Well, we've got a number of topics that we want to get through in this course today. There are 6 modules, each one available as a separate video for you to watch. So I suggest you watch them in order and perhaps take a little bit of time to reflect between each module to make sure you've absorbed everything. We're going to start with a discussion of tables and views and how we might think about implementing those in a database, kind of fundamental building blocks. Then we'll get on to indexes, stored procedures and functions follow that. Then we'll get into transactions and how we manage to maintain atomic data within our database. We'll talk a little bit about the newer in-memory technologies that are available in SQL Server 2014. And then we'll wrap up with a module on optimizing and troubleshooting. So there's a lot of ground to cover today, and hopefully a lot of that will be useful to you. And why will it be useful to you? Well, because what we're trying to do is to, first of all, help people who want to implement databases. So if you're out there and you're perhaps in your job role, you're a developer or you're a database professional and you need to implement a database for an application, hopefully you'll get a lot of good guidance and tips in this class to help you. The other reason that we wanted to create this course is for people who are pursuing certification, and in particular, if you're preparing for the equivalent exam to this course, the Implementing SQL Server Databases exam, then we wanted to provide you with some information to help you do that. Now, I would suggest to you, don't watch this video this morning and then go and do the exam this afternoon, because we're not in the course of, even within the 6 modules we've got, we're not going to be able to cover everything you would need to know to pass the exam. But hopefully we can bring out some of the kind of key points for you to think about and point you off and reference some other material that you can use to help you prepare. And some of that other material to help you as you either prepare for the exam or as you learn to use SQL Server, we've listed on the slide here. There's some suggested supporting material. We have classroom-based training, Microsoft official curriculum, or MOOC as it's called, courses. You can attend a MOOC course at your local CPLS, and we have Microsoft certified trainers throughout the world who are trained and who are experts in delivering content in a more relaxed, longer-term type engagement in a classroom with other students where you can study and learn. So that's a really good option if you learn best in a classroom with an instructor. If you want to learn online, if you want to do this as a more self-paced thing, there are lots of other courses on the MVA. So I suggest you have a look on the Microsoft Virtual Academy site. You can filter by technology. If you filter by SQL Server, you'll see there's a whole bunch of courses there. The other thing I would suggest you do, just flicking onto another slide here, SQL Server, if you've been working with SQL Server for any length of time at all, you probably already know this, but if you haven't, or if you're new to the platform, SQL Server Books Online, or BOL, you'll sometimes see it referred to, is the definitive product documentation for the product. And it's not just documentation in terms of how to use the product. There's guidance and information in there about how to get best use out of it. It's available online on both the TechNet and MSDN websites, and you can download a local version. When you install SQL Server, you can install the documentation locally. I do suggest that you use the online version where possible, because obviously it gets updated and the latest and greatest information will be there. Just to kind of show you what it looks like, I'm just going to flick around. Here's the TechNet version of the site. You can see if you look in the TechNet library and drill down into the product documentation, you'll find books online for SQL Server 2014, and there's the equivalent for other versions as well that you can go to. And if you're not a TechNet aficionado, if you're more on the developer side of things, the same thing is on the MSDN website as well. So you'll find exactly the same structure and the same documentation there. So I do suggest you check that out. Okay, just returning to the slides. If I can get to the right window, there we go. So that's the documentation. I do suggest you use that to supplement whatever training or whatever learning you're doing. There's lots of great information there. And every developer in SQL Server, when they get stuck with the syntax, that's the first place you go. You look in books online. You're on the MVA. That's currently where you are, just in case you weren't paying attention. You're on the MVA website and you're currently viewing this course. The Virtual Academy is more than just a collection of videos. I do suggest you participate in the community, sign up there. You can build up a collection of points and interact with the community there. And learn an awful lot from the various different courses that are in the MVA. So I do suggest keep coming back. There's going to be lots and lots of new courses appearing, and as new versions of technologies come along, we'll be publishing training as quickly as we can. So it's a great place to stay up to date. So that's the introductions. We're ready to jump straight into the first module, and what we're going to do is talk a little bit about implementing tables and views. And I'm going to hand over to Christian because he's the expert. So Christian, take it away and tell us what we're going to be talking about in this module.
Great, thanks Graham. So I just wanted to reiterate the fact, first of all, that the aim of this course and this module was really to help you prepare towards the Developing Microsoft SQL Server Databases exam. It's not completely self-contained in terms of it providing everything that you would need to take the course, but what we've done in developing the materials and the plan for these modules is really to pick out the areas that we feel as trainers that can be confusing sometimes for people, and also areas of specific interest that may be harder for you to study for on your own, that you may get more kind of support with through demos and discussions throughout the day. So we'll first start talking about tables, schemas and views. Then we're going to have a discussion around temporary tables and table variables. So these are programming constructs, if you like, that are often cause for much debate, and we'll compare and contrast how they're used in that part of the module. And then we're going to talk about common table expressions, is something that will be is definitely part of the exam syllabus, if you like, and we'll talk about that and some demos of that before talking about table partitioning, which again is another really important part of the syllabus for the exam, and is often misunderstood and overlooked, and be quite difficult if you're studying on your own to grasp some of those concepts.
Sounds good. So there's a lot to cover. Let's dive in and talk a little bit about designing tables.
Sure. So the topic of designing tables itself we could talk about for many, many days. So what I wanted to do first of all is have this kind of introduction and reminder for those of you that have been working with SQL Server for a while. And we'll talk about some discussion points and things that you should bear in mind. And the first one there is really to avoid table names and column names that contain spaces, keywords and symbols. And this is really to help SQL Server and to aid your development, where you can use some of these, but you'll have to put them in square brackets to tell SQL Server not to treat them as keywords. But so as a best practice, it's really good to keep object names simple.
So I should probably avoid things like, I guess, data type names. So don't have a column called date or date time, because that's the name of a data type.
Yeah, exactly. Or a table called table.
Oh, yeah, good point. I guess if I was running a furniture store, I might have a table called table or something like that. Yeah, okay. So good tip. What else?
So the next one is to plan data types for each column. So your data types really control the type of data that you can have within the column, within your table. But it's not just as simple as saying, I want numbers to go into this column. So if you were representing a number, you might use the integer data type, but we have a tiny int, we have a big int, we have the integer data type, and they allow for different sizes. So it's important that you plan not just for what you think you need, but your kind of capacity and growth expectations around the data types, and use those appropriately.
And I guess as well, we talked about numerical data types and getting the size of the integer right. I guess with strings or with text data, you want to think about whether it's a fixed length or a variable length and consider that as well.
Yes, yeah, absolutely.
Okay, great.
So the next one is planning to whether to allow nulls. So a null is the absence of any data rather than being zero. And what's interesting about nulls, or what you need to bear in mind, is that you can't do calculations on nulls. So we kind of have to handle them a little bit differently within the code. So it's a good idea to try and avoid nulls, but there are a lot of situations, and there'll be debates around designing tables and schemas. So, for example, it'd be quite easy to not allow null on somebody's age, for example, because everybody has an age. But if you were storing a record of a person and you didn't know what their date of birth was, it may be more appropriate to have a null value, an absence of a value, than make up something like, I don't know, 1st of January 1900 or something, the absence of data. So it's important that you plan for your use of nulls and try and avoid them if it's appropriate, because it will make your life easier.
Sure, and the thing I quite often point out about nulls is, to a certain extent, null means we don't know what the value here is.
Yeah.
And one of the things you'll find as you're developing a database, if you have got nulls in the database, it makes checking for equality very difficult. Find people who have the same last name. Well, is that unknown last name the same as that unknown last name? Well, we don't know, because we don't know what the last names are. So you have to be pretty careful about deciding when it's appropriate to use null.
Yeah, exactly. And that's the important thing. It's not sufficient to say, I'm not going to allow nulls on everything generally, because there are situations where it's better to have a null rather than to make up a value.
Okay.
So the next one is really around planning your primary key and foreign key constraints. And again, this is an area that we could talk about for several hours, but primary keys and foreign keys are how SQL Server helps you to maintain the referential integrity of your data. And by that, I mean, we'll have a look in a demo shortly, but we're talking about grouping together related data like customers and orders and order details. We'll have a look at more detail in the demo coming up around that.
Fantastic.
And the final one is really around planning indexes to optimize performance. So again, indexing is coming up in the next module. We'll talk about it in a bit more depth, but it's definitely a really important area when you're thinking about designing your tables, is how you're going to be accessing those tables and what appropriate indexes would be to improve the performance on those tables.
Great. And as you say, there's a whole module on indexing coming up. Yeah. But when you're creating a table at that point, you may initially think about, well, I want to have an index on, say, the primary key column, or a column that's frequently searched. Or
exactly, whatever. Yeah. So it's important to bear it in mind right at the beginning.
Great. Okay, brilliant. Well, with that, you'll see quite a few of these slides today. We're going to try and show you as much of this stuff as we can. So it's a demo that we're going to jump to. And with that, we'll switch across to Christian's machine, and he can show you how this works.
Great. Thanks, Graham. So in this demo, first of all, we're going to create a new database called DemoDB, just to provide a new context for the setup. Then we're going to use DemoDB. So the first statement we're going to look at is this create table. So we're going to create a table called customer. So this is within a schema called DBO, and we're going to talk about schemas in the next section. And within this customer table, we've first of all got a column called customer ID, which we can see has a data type of integer, which we use int for short, but it's also been set as an identity column. So this means that we're not going to have to supply a value for this. SQL Server is automatically going to generate a value as we insert this, and we'll use this for identifying the rows.
And the identity, I see you've got 1, 1 there, so it's going to start at 1 and go up in ones.
Yeah, okay. Exactly. And we'll also specify this as a primary key, and then we're going to create another table to reference that primary key.
Okay.
So the other column we have here is customer name, and that has a data type of nvarchar or nvarchar, and this basically means we have a variable length character field of up to 50 characters. Now the N means that we can store Unicode data, so characters from other languages, basically special characters.
So kanji characters or whatever.
Yeah, exactly.
And there's a varchar equivalent, which is just your straightforward ASCII values. Yeah.
So the way to think about nvarchar is that it's twice as much to store Unicode data, so nvarchar, as it is to store varchar. But if you're looking at international data sets, or you don't know if you're going to involve international data sets, particularly with names and different characters within names, it's better to err on the side of using Unicode data types. We're also specifying customer name as not null. Remember we just talked about not null, because there's no point having a record that for a customer that doesn't have a customer name. So let's go ahead and create that table.
And just while you're creating that, just to kind of point out, this is a fairly simple demo. We've got customer name there, so we've obviously got the entire customer name first and last in the one column. In reality, that's not how we would design a database.
Yes, yeah, correct. It's fine for the purposes of a demo, obviously, but there's a whole domain around this called normalization, and if we were to design this table to third normal form, we would separate out customer name because it's multiple values within a single column, and we don't want to do that if we're designing to third normal form. So I would definitely encourage you to go and have a look at the topic of normalization, and particularly with third normal form, which is what we tend to design tables to.
So if you're preparing for the exam, then clearly a little bit about understanding how you would normalize the schema of a database to separate out your data into multiple tables and columns.
Exactly. And you can imagine a very fair exam question asking you to normalize a schema design, so you need to be familiar with what that means.
Okay, fantastic.
So this next statement here, we're going to insert some values into the customer table. So this insert statement, you notice that I'm specifying two values in here, two customer names. I'm not having to specify a customer ID because it's an identity column. You remember I mentioned that SQL Server will automatically generate those values for us.
So I guess what's interesting about the insert statement is, a lot of the time you're used to seeing an insert statement that just inserts one row.
Yeah.
In this case, we're using one insert statement to insert two rows. Each of those rows in the table will actually have two values, but because one of them is an identity, we don't have to explicitly specify.
Yeah.
Right.
So then the next table we're creating here is a customer order table. So let's have a look at that. So we're creating another ID column. And for this is also an identity column, and we're starting that from 1,000,001, and we'll increase that by 1. This is also the primary key.
Okay.
We're also creating a customer ID column. You remember we have a customer ID in the customer table as well up here.
Yep.
And what we're saying is that this customer ID column is a foreign key that references the customer table we've just created based on customer ID. So we're creating a relationship between this value in this table and customer ID in the customer table.
And I guess it's worth pointing out that's a kind of key, if you pardon the pun, it's a core part of database design. The reason it's a relational database is because we have multiple tables, which sometimes we call relations, and there are relationships between them. Yeah.
Yeah. So, and this is where we use primary keys and foreign keys to help to ask SQL Server effectively to help us maintain referential integrity. So this is the term when we talk about primary keys and foreign keys, is referential integrity. If you want to kind of follow that up and really understand what we mean by that. And you could maintain referential integrity yourself in the application layer. You could enforce the data structures there, but it's much easier generally to get SQL Server to handle that for you.
Okay.
And we're also creating another column here called order amount, which has a decimal data type, which is going to allow for 18 numbers and then 2 numbers after a decimal point.
Oh, so you're expecting fairly big orders then?
Hopefully.
Oh, okay.
I'm betting on the future. Okay, so that was created successfully. So now if we have a look at our customer table, so we have those two names that we created, automatically generated customer IDs. Mm-hmm. Now I'm going to insert some values into my customer orders table.
Okay.
So if we look back at the structure of that table, remember we've got customer order ID, so we're not specifying a value for that because it's an identity column. Okay. Then we've got to specify a customer ID, so this is the first value here, and then the order amount. Okay. So I'm creating two orders, one for customer 1 and one for customer 2.
And if I wanted to insert an order ID, if I had a specific order ID I wanted to insert, can I override the identity? Is there a way of doing that?
I don't know, actually. Can you enforce that?
You can set identity off.
Yes, yeah. Yes, correct. Yeah. I mean, so that's a way for controlling if you're removing data and adding data later on, you could override that insert. Right. But you need to be very careful about what's being created.
Absolutely, yeah.
So where did we get to? Did we insert these? Oh, I've inserted
we've doubled up because I distracted you, but that's
there
okay.
There you go. No, that's fine. So we've got some extra orders here. So now I'm going to insert another row in here. I'm going to try to, but you notice this is customer ID of 3, which we haven't created.
Okay.
So this is giving us this error message because we're in violation of the foreign key constraint. So what we've specified is because we have a foreign key back to the primary key on the customer table, I can't have orders that aren't referenced to a customer, which is valid in this kind of business scenario.
So, and you didn't explicitly create a foreign key with that name, it's generated that.
Yes, it's
kind
exactly.
of weird name there.
It's automatically generated that name there. Okay. So the next part of the demo, so we're going to try and delete a customer. So we've got customer ID 1, which we know we've created. They've asked to be removed from our mailing list. They're not interested in having, being a customer anymore.
Okay.
Sorry, scroll down there. But what it's telling me is that, again, I'm in violation of this foreign key constraint. That's because the customer that we're trying to remove still has orders in the orders table. So, and if we were able to remove this customer, we'd have some orphaned orders that we couldn't track back to work out who ordered them.
And just to be clear, it's not just because there is a foreign key constraint. If the customer didn't have any orders, then there wouldn't be a problem. We could delete them.
Correct. Yeah. Okay. It's because there's a relationship with data in the other table.
I see.
So what we're going to do in this next part, we're going to alter table. We're going to alter table customer order. We're going to drop the constraint. So the foreign key that we created when we defined the table, we refer to as a constraint because it constrains the data that can go into that column. I took a copy of that foreign key name that was automatically generated.
This is the issue when it automatically generates the name. You don't know ahead of time. Yeah,
exactly. So we'll drop that constraint. And then we're going to alter the customer order table again. We're going to add the constraint so we can control the naming of that foreign key this time. So we're specifying exactly the same things, that it's a foreign key on customer ID, which references the customer table, customer ID column. But this time we're going to add an on-delete cascade.
Okay.
So I'll explain what that means in a minute. So now we've re-added that foreign key constraint. Look at the customer orders table. So the customer orders table, we have customer ID 1 has two orders within this table. And if we try and delete that customer now, so we noticed it failed before, but because we've created the foreign key constraint with an on-delete cascade, what it means is we've removed the customer, but we've also removed the orders that were associated to that customer.
Okay.
So this is quite a powerful option, and with great power comes great responsibility, in the fact that if you make a mistake on that, then it's going to cascade your deletes through the rest of your data. Generally, when we're working with applications in environments, it's an unusual event to remove data. So we would generally not use on-delete cascade because we're trying to mitigate any risk, basically. But it's a very useful feature as long as you've got the confidence that you can control its use, basically.
And I guess it's worth pointing out that there's an equivalent for update. We can do updates cascade. Yeah. So in a slightly bizarre scenario, if I changed a customer's ID, I could then change the matching ID in the orders table as well, which is even less common a scenario, I guess, than deleting.
Yeah. But I mean, it's definitely important. And again, when we're looking at features like this and the way that you can use the language and the constructs, you need to be aware of what's possible more than, we're not saying that this is how you should do it, but certainly for everyday use and for the purposes of the exam, you need to be aware of these features and how you could design it for very specific scenarios.
Great, okay. Well, just before we move away from the demo, I did want to drill into one more thing, just in a little bit more depth. Could you possibly scroll back up to the create table statement?
Sure.
Fundamentally this module is about creating tables, so let's talk a little bit more about that. And there it is, okay.
Can we go for this one?
Yep, that's fine. So we have this create table statement. The syntax is create table, the name of the table, including the schema. And that's we'll talk about schemas later on, but it's worth getting into the habit, I guess, to explicitly specify the schema and the table name. And then for each of the different columns that we're defining in that table, we've got a name, a data type, and then if there's additional attributes of that column that we want to include, like this one's an identity column and it's the primary key, so we specify them. What we haven't done here is explicitly said, well, where physically on the disk should the data in this table be stored? And that might be something I'd want to do. I might have a table that's accessed frequently and I want to make sure it's stored on a solid state drive, and a table that's perhaps archived data that I'm quite happy to store on a mechanical drive.
Yeah.
Can you talk to me a little bit about how I manage that storage?
Sure. So the feature within SQL Server to manage that is called file groups.
Okay.
So if we have a look in, do we still have this?
DemoDB, you probably have to refresh your list of databases, I think, in Object Explorer. There you go.
So if we have a look at the properties of DemoDB, what we'll see here is that we've got one of these tabs called File Groups. So we have one file group called Primary, so you'll always have this when you create a database. And this basically contains the MDF, so the master data file that you would have for any database. Okay. And if you wanted to create additional file groups, we could create one called... so should we call that fast disk? And then if we switch over to files, and we wanted to add another file, let's call that, we'll call that fast disk file. And then I'm going to specify, I'm going to put this in the fast disk file group.
Okay.
And then I don't actually have any other drives on here, but essentially what I would do is to specify
where
I'm going to put it on a fast drive and an SSD disk. Sure. And then when I'm creating the table, I would create it on the fast disk file group.
And that's literally the syntax at the end of the create table statement is on and the name of the file group.
Exactly.
So, and I guess again, if you are preparing for the exam, one thing to think about here, we're not going to dive into file groups in any more depth in this course. I do suggest you go and look at the documentation, and one of the things you would probably want to do in a database is use that primary file group that's there by default for the system tables that the database uses to maintain its own metadata, but then explicitly create file groups for the data that you want to create, where you want to create your tables, and make one of those the default, so that even if you don't specify on which file group, that's where it would go. So do go and look up file groups in the documentation. There's a lot of good stuff in there.
Absolutely. It's a good best practice to not use the primary file group.
Yeah.
When we look at recovery options, I think is in the next course that we do, because you can do recovery of specific files and file groups, and if you've grouped everything into different file groups, it can allow you a bit more flexibility in how to do that.
Okay, great. So let's draw our attention to schemas. We saw some in the example there, or at least we saw the DBO schema.
Yeah.
Tell us a little bit more about schemas.
So the idea behind schemas, first of all, where we use schemas is for a naming boundary. So it's a way for us to logically group database objects, and this is where we talked about using the schema name when referencing objects before, and this is really important when we talk about name resolution of objects.
So in theory, I mean, we've got the fully qualified name, if you like, down there is actually the SQL Server instance that the thing is on, the database. Usually you skip that because normally you're working within a specific database. That's the context that you're working within. But then within that, I've got schemas and objects. So I could, in theory, have a sales schema that has products in it, and I could have a production schema that also has products in it. So it's the fully qualified name. Yeah. Both parts makes it unique.
Exactly. And, interesting areas. So this is what we call a 4-part name that we've got on the slide there. And as you mentioned, Graham, so we would normally reference the schema in the object because we're in the context of a database, in the context of a server. So you could specify the whole thing, but generally we would use a schema and object name. And interesting areas where we've used this in the past, or I've seen it used, is a development schema and a production schema is a way of having kind of naming boundaries. And if you see anything in a development schema on a production server, you knew something's gone wrong in moving the code from development into production environments.
Good enough.
So it's a way of providing a naming boundary of there may be grouping around business functions or the way that you use the database or the application itself.
Okay, great. So.
And the next part is really around a security boundary, so we can apply specific security to schemas. So if you wanted to provide access for a new user to everything within a specific schema, or a set of tables and objects, you would put them within a schema, and it makes it easier to be more specific about the security and an access that we want to provide to users. And here's an example at the bottom of the slide where we can use grant execute command to allow somebody to execute any code that's part of the sales schema.
So I guess in this example, if I had multiple store procedures in there, rather than explicitly granting execute on each individual store procedure, granting it on the schema, it then inherits that permission.
Yes,
again.
exactly.
Okay.
Exactly.
All right, so tell me a little bit about, we talked about the naming boundaries. Tell me about how SQL Server goes about resolving cases where I don't specify the schema.
Yeah, so this is a really important point. A performance tuning tip is around this default schema and naming resolution. So if I did a select star from table, for example, and I didn't specify the schema, what SQL Server will do is first of all have a look at your default schema, if you've got a default schema defined. And if that object doesn't exist within your default schema, then we'll try the DBO schema. And if it doesn't exist within the DBO schema, then we'll return an object not found. So that's fine and that's straightforward and easy to follow, but where we've seen this cause a problem, and again, and this leads on to this tip around always use this 2-part naming convention of schema and object name, is really in scalability. If you have a user in the sales schema and it is referencing an object in the DBO schema, it will work. and you won't notice any different, and it's very, very fast. But you scale that up to thousands of users and thousands of transactions, all of a sudden this extra check of is it in the default schema, no, let me check the DBO schema, can cause significant scalability issues. So it's best, no matter how small, to start with this two-part naming convention, because as you scale, you'll be very pleased that you started off as a best practice.
I guess it's like anything else. I always say to people who are developing anything in SQL Server, yes, there's default behavior for everything, but it's best to be explicit. So when you're creating a table, depending on the way that you've configured the database, it will either allow nulls or it won't, and you don't have to specify, but it's best to be explicit. It's best to be clear about what you want. And the same is true when you're dealing with objects. It's best to be clear it's that object in that schema that I want to access. Okay, great.
Yeah, exactly. It's one of the benefits and detriments to SQL Server in a lot of things just work, but what you need to appreciate is what goes in the background to make it look like it works. So if you can be very specific about what you're asking it to do, you're not relying on SQL Server or giving it extra work to do to try and to make it work for you.
Okay, great, thanks. So, hey, I told you we'd see a lot of these slides. We've got another demo, and you're going to show us exactly how schemas work. So let's switch to the demo machine.
So within DemoDB, I'm going to create, so we have this create schema statement here. I'm going to create a new schema called reporting, and authorization effectively is going to I'm telling SQL Server that I want the DBO, so the database owner user within the database, to own the reporting schema.
And I guess it's just worth pointing out, obviously you and I have worked with SQL Server for more years than I care to remember, but for those of you who haven't, this can be a little point of confusion, so let me just pull this out. There is a schema called DBO in every database, and there is also a user called DBO in every database.
That's a good point.
Historically, that's because I think prior to version SQL Server 2005, objects were named after whoever owned them, whichever user owned the object. So there was always a DBO, which stands for database owner, and the DBO would own objects that were created by an administrator. To bring this in line with more kind of standards across multiple database systems, the ideas of schemas were introduced in SQL Server 2005, but obviously to maintain compatibility with code from earlier versions of SQL, we still had this notion of a user called DBO, so we created a schema called DBO so that code would continue to work. So the potential point of confusion, and I hope I haven't confused you even more, but there is always a user called DBO, which is think of it as being about the administrative user for that database. It's the database owner. But there is also a matching schema called DBO, and it's useful not to get the two of them mixed up.
It's a very good point, actually, and yeah, I can appreciate how I could have made assumptions there, because like you said, in older versions of SQL Server, before we had schemas, we still had this two-part naming conventions, but it was actually the owner of the object. And then the concept of schemas came in, which was much broader than the owner. It was more kind of grouping of objects. But to maintain backwards compatibility, we still have these constructs of DBO and these uses.
Sure.
So what I'm saying here is I'm creating a schema called reporting, which is owned by the DBO user within the DemoDB database.
Great.
So I'm also going to create a schema called operations, owned by DBO. But because I'm executing this as a single statement, the flights table should hopefully be within the operations schema.
Okay.
Good. Well, that worked. And we'll go and have a look at that now. So we can see we have operations flights here, which is what we expected. So we have the flights table created in the operations schema. And we should also have...
Under security.
Oh, there we go, thank you. The schemas, so we have the operations schema and the reporting schema that we created as a separate event. So let's drop that table. and drop the operation schema.
Okay.
So now I'm going to execute these separately. So I'm going to create a schema called operations,
Okay.
which if we refresh that, I still have...
It's still there, yeah.
Yeah, operations schema. Then I'm going to create a table called flights.
Okay.
So if we have a look for this table again now, you notice it's been created in the DBO schema, and that's because my default schema is DBO, and that's exactly where it's gone because I didn't specify the schema to create it in.
Or indeed, if you didn't have a default schema, it would default to DBO,
yeah.
the default, if you like.
Yeah, exactly. And the other interesting point that I wanted to put at the end here is this exact same table I'm going to create again in the reporting schema, and this is where you need to be careful, and it helps for you to be specific about the schema you're referring to. I have two tables in this database called flights, one in the DBO schema and one in the reporting schema.
So back to the example on the slide, if I did a select star from, well, I wouldn't do select star, I'd do select the columns I want because that's the best practice, from flights, the specific flights table it would query is going to depend on whether or not my default schema is reporting or DBO, or I don't have a default schema.
Exactly. So you could end up getting having to troubleshoot a problem where you're not seeing the data you expect, and that's because you weren't specific about the schema that you wanted to reference.
Fantastic, thanks. And we'll move on from that demo and talk about views. So we've talked about tables. I kind of get tables are where the data is stored. Tell me a little bit about views.
So a view you can think about as a virtual table within the database. So it's an object that's referenced in the same way as a table. So you would do select column names from a view name, and there's nothing from that query. You wouldn't know whether that was a table or a view. And then when we're creating the view itself, is basically you're creating a view based on a select query. So if we have a look at the code on the screen now, so we have this create view statement. We're following best practice. We've got human resources schema here, and we're creating a view called employee list based on that select statement.
Okay, so and I'm guessing, I mean, with the select statement here, it's fairly simple. We're selecting some columns from one underlying table. I'm guessing I could have views that are based on multiple underlying tables.
Exactly. And this is can be quite powerful with views in the fact that select statement could have a join to bring a single result set, and then you would use that as if it was a single table.
Okay, great, thanks.
So moving on to more detail around the views. So a view doesn't persist data unless you have an indexed view. So an indexed view, we'll come on to that point actually. So if you think about normal views, it doesn't persist the data. So the data doesn't exist. And when you reference that view, it will pull the data from the underlying tables.
So that the query in the view definition is executed when I query the view.
Exactly, right, in order to return the data to you. So another point to mention around here as well is this with schema binding option. So if you think about the scenario where you create a view that's used by your application, selects a number of columns, and you're presenting that through your application, if somebody removes a column from the underlying table that your view is dependent on, that view is then broken. Okay. So what we would do is to create a view with schema binding to prevent schema changes to the underlying table from breaking the views that we're using.
So it prevents changes to the definition of the underlying table. I can still add and delete data directly at the table.
Absolutely.
Yeah,
absolutely.
Sure. Okay.
So it means that the columns that I have in the view can't be removed from the underlying table because it would break the views. So it's very common to use schema binding for important views.
Okay.
So the next point that I wanted to make here was if you add a unique clustered index, and we're going to talk about indexes in the next module, if you add a unique clustered index to a view, it will make it an indexed view. And what's interesting for that is that it then persists the data independently.
Okay, so independently of the table.
Of the table and the view. So the view is a virtual table, and we mentioned before that when you select data from that view, it selects it from the underlying table. But if we put a clustered index on that view, it's actually going to generate a new physical table, effectively, called an indexed view.
Right, okay. Oh, so there's a point there to talk about that.
Yeah,
okay.
That's fine. So it's persisted to disk in its own right to improve performance. Because if you've got to do calculations within that view, you can pre-calculate them and have them persisted on disk.
Oh, so I could, for example, have an orders table that has, I don't know, the price and the tax, and then calculate the total price.
Yeah, exactly.
Right, okay.
So so an indexed view, it's again, great power comes great responsibility, not to overdo indexed views. And there could be an argument for saying, if I need an indexed view, should I really does it mean that I haven't designed my schema properly?
Sure.
If I'm having to create these new constructs? But something that's very important for you to remember in general, and certainly for the exam, is around this concept of an indexed view. And Enterprise Edition has a feature where the optimizer within Enterprise Edition will automatically use indexed views to improve the performance of other queries. So it will treat it exactly what it is, as an index, and it will use an indexed view to improve the performance of other features.
Oh, okay.
But you only get that with Enterprise Edition features.
Right.
With the Enterprise Edition feature. So you can imagine, an exam scenario, an exam question where you have Standard Edition, you can see where it's leading you with this indexed view, but you don't have Enterprise Edition, so SQL Server won't automatically use this indexed view to improve the performance of the other queries.
Okay, just to be clear, I can create index views in Standard Edition.
Yes.
It's just the optimizer doesn't.
Exactly. So you can create the index views, and the application that you're creating the indexed view for, you would use that very successfully. But the Enterprise Edition will then use that in other areas of the application in SQL Server.
Okay, good enough.
So, and the final point there is the inserts and updates. So we can use views to do inserts and updates to the underlying tables,
okay.
But not if it was based on multiple tables.
Oh, well, I guess more specifically, if it's based on multiple underlying tables, I can do an update to the view which affects only one of those tables.
Yes, sorry, yes, correct, yeah.
But I can't. So if I had a view that showed me customers and orders combined, I couldn't do an update that changed a customer's name and changed an order at the same time.
Yeah, correct.
Okay. Well, you're up again. It's time for another demo. You're going to show us a little bit about views. So let's switch across.
So in this demo, we're going to use the AdventureWorks database, which is the kind of default sample database that you'll see if you've been doing lots of different training courses. And I'm going to create a new view in the person schema, which is called individuals with email, which is going to be based on this select statement.
So this one is based on two underlying tables then?
Yes, yeah. Right. So I can execute that select statement. And basically what I'm saying when I'm creating this view is this kind of predefined select statement. So I create this view of individuals with emails, and when I query that view, that's the equivalent of me executing this select statement here.
Okay, so from the point of view of creating, I guess, an abstraction layer for an application, the application developer can write much simpler queries because the views encapsulate the more complex transactions. Okay.
So, so what this then enables us to do, like you said, the simplification of it, I could do a select star from, naughty me, I should have done the all the columns as best practice.
We'll forgive you in the day.
So a select star from individuals with email, but then I can order it by last name, so I can reorder the results, I can aggregate the results, I can do anything that I want with it effectively.
So it is, I mean, it's very exactly the same as querying a table.
Yes, yeah, exactly. It just makes things a bit simpler, basically. So I can also have a look at the definition of this view here. So by using this statement here, what I'm saying is, show me the construct of this view, which is giving me this create view statement. And I could get the same thing by going to the AdventureWorks database, person individuals with email, and I could do this script view as create. It's going to give me the definition that I created. And the reason that I wanted to show you this was really to move on to this with encryption option that you have here. So essentially what this will enable you to do is to hide the definition of the view to stop people scripting it out.
So it's quite confusing terminology, because just looking at that, if I didn't know any better, I would assume that meant the data will be encrypted.
Okay.
But of course it doesn't mean that at all.
Yeah, absolutely. So it's the definition of the view that's encrypted here. So if I do that same view definition, you'll find that we actually get a null result here. So, and what you'll find is, this feature will be used for companies that write software for SQL Server that they then sell to customers, and they might not want their complex IP that was written in within a view to be scriptable by other people for reuse. So they might use the with encryption keyword.
So they're protecting themselves from intellectual theft, I guess.
Yes, yeah, exactly. And, I don't see it used very often because it can make troubleshooting difficult. Sure. But certainly as a feature and an option within the product, it's something that you need to be aware of. And, if you were troubleshooting and you were trying to script this out and finding that you were getting null results, if you knew that there was this with encryption keyword there, it will help to put the pieces together and not think SQL Server's broken because I can't script out this view.
Okay.
So again, let's drop that. And we've done this one already. So if we have a look at any of these other ones, and this script view as is most often what I would use if I'm kind of troubleshooting and looking at definitions of views and store procedures and anything like that.
It's just this ability to script things using the user interface in SQL Server Management Studio is one of these features that I really love. I remember working with a guy who was an Exchange Server administrator, and he would have killed to be able to point at things in the Exchange UI and just script the PowerShell that's required to create them. So fantastic, great. That was views. Now, views we thought of as being kind of virtual tables. Now we're going to talk about something slightly different. We're going to talk about temporary tables.
Temporary tables. So temporary tables is a very common and useful topic within SQL Server. And remember, this section we're going to compare and contrast temporary tables and table variables. Okay. So let's look at temporary tables first. So temporary tables are used to hold temporary result sets within a user's session. So effectively, if you wanted to create a loading table, you would put that within tempdb, because tempdb we would use like a scratch database. When SQL Server restarts, tempdb is effectively recreated. So all of these temporary tables would be gone. They're not kind of persisted beyond reboots.
Just very much a sort of workspace.
Yeah,
too, right?
exactly,
okay.
exactly. So they're created in tempdb, they're deleted automatically. So if you create it, like we have in the example here, we have a hash or is it a pound in the US?
Our American cousins would call it a pound symbol. I would call it although hashtag has become the thing, so it's a little confusing.
So TMP products. So create table hash TMP products would create a locally scoped temporary table. And if we used two hashes, that would be a global temporary table.
And so the difference, the difference being?
So with a single hash that we have in the bullet on there, it's scoped to the session that you're in. So that table will exist while you're executing in the session that
connection that you've opened.
Yeah, that connects to SQL Server, but only you will be able to access it. But the next bullet here, which has the double hash prefix, will create a global temporary table. So any session will be able to reference that global temporary table. It's not something that has much of a use case scenario these days. So mostly we would use locally scoped temporary tables, because if you had a table that you wanted multiple user sessions to be able to access, then you generally create a normal table anyway.
Okay.
It can be quite difficult to troubleshoot and provide, access to global temporary tables.
Okay, great. So that's temporary tables. You said we were going to compare them to table variables, so let's look at those.
Sure. So table variables were introduced around SQL 7, SQL 2000, something around that kind of time frame. And they were introduced because of the nature of temporary tables. They're basically like normal tables in a normal database. And SQL Server maintains what's called a set of statistics, and again we'll talk about that in the next module. So statistics contain data about the distribution of data within the table, and as the data within the table changes, the distribution data changes, statistics will get automatically updated, and when statistics are updated, it can generate a recompilation of the code that you were using, which can then give you a different execution plan. So it can cause performance problems generally.
You're creating a lot of additional work unnecessarily because the tables are temporary anyway.
Exactly.
Okay.
So then this the concept of a table variable was brought in, which is used similarly to temporary tables, but it's scoped to a batch. So it's scoped to a piece of code that you're running rather than the whole session.
Okay.
It will make more sense when we have a look at the demo.
All right.
But the key thing to realise with table variables is that there are no statistics on table variables. So the fact that there are no statistics means that changes don't cause recompilations of the code using those table variables, which can be a good thing if recompilations is a problem. But because on the next bullet, the estimates are always one row, it can be very effective for small data sets. Because if you've got 10 rows and the optimizer estimates one row coming out of that table, then that's fine. But if you've got 100,000 rows and the optimizer expects one row, that can change the way that SQL Server optimizes the code that you're running.
And I'm going to guess, to use that example, it's an extreme example, but if you're designing a database and you've got a variable that's going to hold 10,000 rows, then I think there's probably more fundamental problems with your database design, I think.
Yes, but I mean, we see a lot of customers that we deal with when we're troubleshooting and looking at health check scenarios and the way things have been developed, where things start off small and you start off with 10 rows, and if you've got 10 rows, table variable is actually quite a useful construct of storing temporary data. But 2 years later, that 10 rows has expanded, it's now 100,000 rows. We've seen scenarios where table variables are great to use and developers just use them everywhere because they seem like they're better than temporary tables. But it's just that they're kind of different, and you need to understand the pros and cons of them both. But in general, table variables only use on very small data sets, and that's because SQL Server doesn't maintain statistics on table variables.
So once again, over to your demo machine, and let's take a look at these two things.
So for this example, I'm going to use a database called People. I'm going to create a temporary table called People, which has all of these columns in. So personal ID, first name, last name, date of birth, date of death, and sex. I'm going to populate the table by inserting into hash people, by selecting the top 250 rows, all of the columns, from a normal table called People.
Okay.
appreciate that the naming may be a little bit confusing here.
Okay.
But
just remember the hash one is the temporary one.
Yes, correct, yeah. So if I have a look at account star from hash people, I have 250 rows. Okay. So what I'm doing here is counting all of the rows within that table. Okay. I have 250 rows in hash people. Now if I disconnect this session, reconnect.
And just to be clear, that even though it's the same window, this is now a different session because we've closed and reopened the connection.
So this table name is invalid because we've disconnected and we've come back with a new session, and because it's scoped to a session, it only existed in the previous session. So I'm going to do the same thing with a table variable now. So in order to create a table variable, I'm going to declare a variable of a table type with the same definitions. So I'll do that, and then I'm going to insert the same code basically, and that failed, and that's because the table variable is scoped to a batch. And the batch is what I've highlighted and just executed.
I see. Okay.
So in order for this to work, I need to declare the variable and insert the rows. Oh.
Nope.
Oh, because I reconnected, I didn't reconnect in the context of the right database.
We're in a different database. I see.
Yeah. So now I've got those 250 rows inserted. And if I do a select, it will fail because it's scoped to the batch.
Okay.
So if I want to work on that table, I have to do everything I want within that single execution.
I see. Okay.
Okay. And if we have a look at the estimated execution plan, I may be jumping ahead a little bit here.
Yeah, estimated number of rows there.
Yeah. So we've got the estimated number of rows for the select.
And it's one. Yeah.
So when in actual fact we know that there are 250 rows, and that may not be enough at this scale to cause the execution plan to be any different. But as I mentioned before, we've seen situations of hundreds of thousands of rows. Later on and causing this problem here.
Oh, okay, great. Thanks for that. Now, common table expressions. This is another way of effectively creating a table-like structure for me to work with. Do you want to talk me through this?
So basically, a common table expression is a mechanism for defining a subquery that can be used elsewhere in a query. So for this example here, it's a bit like a view that's then referenced within the same code.
Okay.
So it can be referenced multiple times in the same query with just the one definition. So for this example here, this select statement that we have in the middle that's wrapped in that with CTE year is then referenced in the subsequent select statement, and then we would do the aggregations or the distinct and count within that.
So in effect, what I'm saying with that with statement is I want to define, for temporary purposes, a table-like structure that's named. I'm giving it a name that I can work with, and then I'm going to reference that throughout the rest of my code.
I'm subsequently going to use. And it's quite a useful construct to reduce the amount of lines that you would put in code. It's not really a performance enhancement. But where we get into recursion, that's where you can really get the performance enhancements for this.
So if I had a table that had, the classic example for recursions is employees who have managers who are also employees.
Exactly.
I can query through and build up build up an org chart.
Exactly. And this is what's coming up in the demo actually.
Oh, well, there you go. And there you go. It supports recursion, and there's a demo. So let's go see the demo.
So I'm just going to use the T-SQL database again. We'll create this common table expression here that we saw on the previous slide. Let's Let's run that. So what that's giving us is in this first definition, we're selecting the year from the order date column as order year and the customer ID from the orders table in the sales schema. Mm-hmm. And then in the second part, we're selecting the order year and we're doing a count of the distinct customer IDs from the CTE that we've defined up here.
Okay.
So what we're looking for is the number of distinct customers that placed orders within 2006, 2007, 2008.
Okay.
Okay.
So that's a fairly simple example.
Yes,
we talked
absolutely.
about recursion, I guess that's what we're going to
Yeah,
say.
so the next one coming up here is this recursive CTE, and this is where the performance benefits of CTEs come in. So what we're doing is creating this anchor query is what we call the start of the tree. So we're doing this select statement from the employees table where the employee ID equals 5. Then we have this union all, and what we're doing is going to recursively go through the CT that we've created based on the employee ID of 5, and then select out that root employee and then everybody that works for them.
So in this sense, just to be clear, we know that employee number 5 is the CEO or managing director
Correct,
of the top of the tree. So we start there and then we'll recursively go down each level of the management hierarchy.
Yeah, exactly. So if we did just select all of the employees, what we're looking for here is employee ID 5, and then we'll recursively go through all of the employees that have a manager ID of 5, basically. Okay. Let's go ahead and run that. So a recursive CTE is definitely something that you should follow up with in terms of preparing for the exam and in general. Being aware of common table expressions in general, but a recursive CTE is really where you're going to get the performance benefits from setting this up.
So as my old teacher at school used to say, it would behoove you to learn a little bit more about this before sitting the exam.
Yes,
so
absolutely.
A little tip. All right, great. Let's switch across. I think we've got one more major topic to talk about on the slides.
Yeah. So partition tables is a really important area of SQL Server, and it was an easy decision to include partition tables in the context of this course because it's really a fundamental performance tuning area for within SQL Server. So this example, we have the sales, the orders table within the sales schema. We've got multiple file groups here, so we talked about file groups, we touched on file groups earlier on, and the idea here is that we are horizontally partitioning the orders table into multiple file groups to make managing a large table more efficient.
So to be clear here, I mean, previously we talked about creating a table and allocating it to a file group.
Yeah.
Here we're talking about creating a table and allocating different partitions within that table to different file groups.
We're effectively splitting a table across multiple file groups and probably multiple files as well to use it most effectively.
Okay.
So this is the idea where each partition would be stored in a specific file group. Indexes are automatically aligned, so this is a great exam tip here around indexes on partitions. A partition aligned index basically means if I created an index on the orders table, it would create indexes for each one of the partitions within the table.
Okay, so it partitions the index as well,
correct,
in alignment with the table.
Yeah.
Right. Okay.
Yeah.
So okay, let's talk about how we would go about creating one of these things then.
Yeah, absolutely. So these are setting up the partition table. Again, from an exam tip perspective, you really need to understand this concept of a partition function. So this partition function defines the boundary values for partitions. So we would typically partition based on dates is a really good typical partitioning scenario, and this boundary values is basically defining, in this example we have here, so this is a date, so this is 1st of January 2000, so this first value that we have here, and we're basically saying anything that this is a boundary value, and between 1st of January 2000, 1st of January 2001, we're going to put them specifically into a partition. So we have in the code, a comment code there.
Yeah, I just want to call out that we've defined 3 boundary points, and if you think about this logically, if you make 3 cuts in something, you end up with 4 pieces.
Yes.
So what you do by defining 3 boundary points is you create 4 partitions.
Yes. Yeah. So we've got everything before 2000. We've got from 2000 to 2001, 2001 to 2002, and anything greater than 2002.
Okay.
As the partition function, and the next part that we would create is a partition scheme. So this effectively maps the file groups to partitions. So this is the next stage from the partition function, and defines a file group for each one of the functions and the next file group that we're going to use.
Right. So we've initially created a partition function. 3 boundary points equals 4 partitions.
Yeah.
We've created a partition scheme, and we've specified 5 file groups because there's 1 for each of those partitions, and then there's one that says, hey, look, if I add some data to this and create a new boundary point, I want you to use this.
This is the next one that I'm going to use, yeah.
Gotcha.
And then when we create a partitioned table, so in this example, we're creating an orders table, we're creating it on the partition function.
Okay. So yes, as simple as that. The create table is create a table where previously we had on file group. It's now on the partition function.
Correct. Yeah.
And we're specifying which of the columns in the table is the one that we compare to the boundary value.
Exactly. Yeah.
Right, okay. Great.
So partition function, partition schemes, definitely something that you'll need to be conversant with for the purpose of the exam.
All right, and I guess having spread the data across these multiple partitions, there's 1 or 2 cool things I can do to manage them. So why don't you talk us through that a little bit? Yeah,
absolutely. And again, definitely from an exam perspective, you need to be familiar with these the different ways you can manage the partitions. Mm-hmm. So the first one that we wanted to talk about is a split partition. So effectively what we're adding in is a new boundary to split a single partition into 2 partitions. So we're saying, in this example here, we're creating, so we're saying for a particular date range, we're going to cut it in the middle and we're going to separate those into 2 partitions.
So the classic example would be from previously, we had a table where the last partition contained all of the orders after the 1st of January 2002. Yeah. Now, if we kept that going for 13 months, we're then into 2003. So what we might want to do is insert a split that says, well,
exactly.
Keep the 2002 on one partition and start using the next one for 2003.
Exactly. So, and the next managing area is around merge partitions. So this is around removing a boundary to merge 2 partitions into a single partition. And you may do this for consolidation of archive data, of older data. So we have this sliding time window that you were mentioning there, where we've split the newer partition. So we've now, we've split 2002, 2003 data. Mm-hmm. 2003 onwards is going on there. But if we look at the other end of this time spectrum, we may then want to merge, in this example here, this kind of pre-2000 orders with 2001 orders, for example.
Yeah, so perhaps I only really care about the most recent 3 years, and then everything else before that just gets lumped together.
Yeah, I still need it, but I'm not worried about optimizing the performance of it, because all of 90%, 99% of my work is at the front end of the table.
Okay, yeah, makes sense.
And finally, switch partitions. So switching partitions is a way for you to switch out. So we have this archive process that we mentioned that we would use maybe merge at the back end of the partition table, and we could use switch to actually switch a partition out of the table completely, to put it into a different table structure. So in this example is exactly that, an archive staging table.
So switching out the old table. It's worth pointing out that $partition function, which is a way of finding out the which of the partitions I want to switch.
Yes,
here's the value, find whichever partition this value's in, and that's the one that I want to switch out.
Yeah, exactly.
Okay. So, for the final time in this module, you're up.
Perfect, right. So for this example, I'm going to, I'll drop DemoDB, because we've been using it previously. I'm just going to create a sample database here. I'm going to create a number of data files and file groups here. So file group, I'm going to create a file group called FG0000 and then a file name associated with that file group, and I'm going to go through and create exactly the same thing for the other date ranges that I have in this table.
So there's nothing specific to partitioning here. This is just file groups we mentioned right at the very beginning of the module. If you haven't worked with file groups before, go and have a look at it. But all we're doing here is creating some file groups and adding files to them.
Exactly. So then the first thing I'm going to do is to create a partition function. So we've mentioned this before as the first thing to do, as range right values. So where I'm saying range right, I'm basically saying how would I deal with a value that was exactly the same as my...
So it's on the boundary.
Yeah, exactly. So if I had a value for the 1st of January 2000, I would store it in the right-hand partition rather than the left-hand partition.
Okay.
So I'm going to create a partition function called PF. Which has 3 partitions. I'm going to create a partition scheme called PS, which has 5 file groups in, which aligns to what I've created. Then I'm going to create this table on the partition scheme, which is on this date key, which gives me my partition table. So now I'm going to insert a few rows of varying values to distribute amongst these partitions.
Okay.
And if we have a look at this partition metadata script,
I guess perhaps just to point out, don't worry too much about the syntax. There's some deep diving into some system tables to find out what's on what's partitioned here,
exactly.
But the point is to look at the results and see how that data has been partitioned.
It's just for the purposes of demos, basically. So what we can see, if I scroll this up, it's showing us the partition scheme, the function, the partition number, and the number of rows in each partition. So based on the rows that we input, it's distributing them amongst partitions 2 and 3.
So yeah, based on the order date key, there have been 2 orders that were placed between 2000 and 2001 there, yes.
Yeah, exactly.
Yeah, which matches well. Yeah, great.
Yeah, perfect. So this one was on the boundary, so
and it's range right, so it's gone into the second one.
Yeah, exactly. So the next thing we're going to do is this split. So what we're going to do is to split, because we've got our last partition is for
2002 onwards.
2002 onwards, yeah. So we're going to split that. Have a look at the partition metadata again. So we've now got a new partition in one of the file groups that we created in the beginning. So we defined all the file groups to begin with.
And it was specifically that last file group that we added when we created the partition scheme. We said, take the partitions from this function, put them on these file groups, and set aside this final one to be the next used one, and that's the one that's used. Yeah. Okay.
So the next one, we're going to merge ranges. So what we're going to do is to merge, so this partition here, partitions 1 and 2, because we're saying I'm not really interested in separating out data between 2000 and 2001. I just want it to be merged into history, basically.
Okay.
So that's what I'm going to do. And if we have a look at this partition scheme data again, we can see that that's been merged, and everything prior to 1st of January 2001 would now be in the first partition.
And the FG 2000 file group is no longer used in this partition table. It's freed up,
exactly.
Nothing on it. Yeah.
Exactly. And then finally, I'm going to create a separate archive staging table. and I'm going to switch out all of this this 2000 data into the archive staging table.
So that's the table you just created. We've swapped the partition with that table across.
Exactly. So if we have a look at the construct of the partition table again,
it's still there, but there's no rows in it.
Yeah, so we've moved those rows out to an archive table.
Okay. I guess just one final point to make about that. The reason we were able to switch between a partition and the table, they were both on the same file group.
Correct, yeah. So if we go back and have a look at that definition there.
Slightly before that, I think.
Yeah.
Yeah.
It was specifically created on the file group there.
And again, without giving anything away, if you're preparing for the exam, be aware that if you are switching between a partition table and either another partition table or just a regular table, they have to be on the same file group for that switch to happen.
Absolutely. So partitioning, and again, it's difficult to do it justice in such a short session, but suffice to say that it's definitely an area that you should get some hands-on practice with and be familiar with these concepts of the order in which to set up partition table and also to manage it with switch and merge. Fantastic.
All right, let's close off and finish over on the slides. And it's been quite a long module. We spent some time at the beginning just introducing the whole course, and then we've covered a lot of ground here. We covered tables and some of the considerations for designing tables, thinking about your data types, your column names, all of that kind of good stuff. Schemas and the idea that it's a naming boundary and getting used to the idea of using that two-part naming approach when you're accessing your tables or when you're working with tables or any objects really. We talked about views. We talked about the idea of that being a kind of virtual table that is the metadata for that view is permanently stored as part of the database, so they're always available for you to query, and they provide an abstraction layer over the underlying tables. And then we compared temporary tables and table variables. Temporary tables exist in the tempdb database, and they are automatically deleted at the end of the session if they're local, or when the server is restarted or the tempdb is reinitialized if they're global ones. Table variables we talked about, and I think the point you made there was they're great for small batches of data.
Yeah, absolutely.
If you start having table variables that have got huge numbers of rows, you might want to think about approaching that slightly differently. Common table expressions, a way of effectively inline defining a table structure and then using that repeatedly in your code. And one of the real benefits of CTEs was the fact that they're a great way to implement recursion. So you anchor the top level thing that you want to query in a CTE, and then you can recursively build out each level underneath that. And then finally, partition tables. And as you said, it's a really key component in optimizing the performance and the manageability of a SQL Server database, and a real key thing to prepare for the exam. So lots and lots of things that we've covered in this module. I hope you've found that useful. Go and give yourself a shake, have a cup of coffee, and make sure that you're comfortable with everything we've covered so far, and then come back and join us for the next module when we'll start looking at indexes. So welcome back. I hope you enjoyed your break. We're back now, having talked about tables and all things kind of tabular in the first module. In module 2, we're going to build on that knowledge, and we're going to talk a little bit about indexes. And I say we, but of course what I really mean is my partner in crime here, Christian. So Christian, what are we going to cover?
Great, thanks Graham. So for this module, we're going to be looking at, first of all, clustered and non-clustered indexes. So the two kind of basic index structures that we have. We're going to look at covering indexes in the include course. So these are very important, both from your wider knowledge, but specifically for the exam. How you can obtain information about your indexes using dynamic management views. And we've got a few scripts and some specific DMVs that are useful to remember. We're going to talk about filtered indexes and how useful they are. We'll talk a little bit around statistics, which support a number of functions within SQL Server and the optimizer, but are very much aligned to index. And then we're going to talk about index maintenance as well.
Okay, so a lot of ground to cover. Let's move on and start looking at some fundamentals.
Let's get started. So in terms of fundamentals, so when SQL Server accesses data, so you do a select statement, very basic select statement, SQL Server will access the data based on a table scan or via an index. So in a table scan, SQL Server will read all of the pages because they're unordered, or they may be ordered, but SQL Server doesn't have any knowledge of the order of that data. And then when using an index, SQL Server will use the index pages to find the specific rows that it's looking for.
Okay, so I guess much like if you were reading a book, you could read it cover to cover,
yeah,
or you could
exactly.
look up what you want to find.
Yeah. And so indexes, we already mentioned in terms of the agenda, so indexes can be clustered or non-clustered, and it's really important fundamentals of working with SQL Server to understand the difference between clustered and non-clustered indexes. And you can create indexes directly with create index statements, or as we saw in the first module when we're creating a table, if we specify a primary key, SQL Server will enforce that primary key by creating a clustered index. So mostly when we're working with clustered indexes, they're created as part of the definition of a primary key on the table.
Oh, okay, right.
So looking at a bit more detail around clustered indexes, so basically the clustered index, the rows are stored in the order in which you specified in the clustered index. So they're stored in a very specific order, and because of that, you can only have one clustered index per table, because it really defines the order of the table itself, and it can't be ordered multiple ways. So when we create a clustered index, it's the table itself that we're referring to.
So there's one clustered index.
One clustered index. Right. So, and a table without a clustered index is what we call a heap. So it's a heap of data, it's unordered data. And while the heap itself isn't an index, understanding this term of a heap, a clustered index, and a non-clustered index is a really important, fundamental part of working with SQL Server.
So a heap might be if I had a bunch of bits of paper with, I don't know, documents with perhaps resumes for employees or something, yeah, and I just dump them on the table, then they're not in any particular order. It's just a heap. It's just a pile.
Exactly.
Of them.
It's
right,
just
okay.
It's just a heap of data.
Okay.
So all data is stored in what we call leaf nodes, and we'll reference this a couple of times when we look at the structures later on in this module.
Okay.
And a clustered index is really a good analogy that I like to think of is the contents page of a book. So you think you pick up a book and you look in the context page, that defines the actual order of the information within the book.
Okay.
So it's the physical ordering effectively of the order of the data within the book.
Okay, great.
Great. So if we then look at operations on clustered indexes, so first of all, we think about an insert. So you're inserting a new row. So it must, in order to maintain the order, it must be inserted into the correct position.
So if I'm just thinking about our book analogy, if that book were, let's say, my address book,
yeah,
and I meet a new contact and I want to keep their details, I'm going to go and find the page where, you know, the A's or the B's or whatever are, and I'm going to put their name in the right place. Okay.
Yeah, exactly. And we have this concept of splitting pages because we've got to put that into the right place. But, you know, with your address book analogy there, you've already filled the pages of Bolton, because you know lots of Boltons.
Yeah.
And you need to insert me. You're going to have to insert a new page in there in order to do that data. And in SQL Server terms, what we would do is to split that page, and we'd have half the data on one, half the data on another.
Okay. I guess in Scotland it would be the M page because you got McDonald's and
yes,
all the rest of the
perfect.
M's. Okay, yeah.
Perfect. And then for an update operation, so the new, so when we do an update, we've got, if you're updating a row, it can either stay in the same place if it will fit,
okay,
but you may be updating data. So we talked about variable length data types before, where we had a varchar 50, and maybe you store 3 characters in there, and everything fits nicely within a data page within SQL Server, and you update that to have 50 characters, and then there's not enough space to store that on that page, so that again causes a page split.
Over. So, and I guess back to my address book analogy, if I've got a friend who changes their cell phone number, well, I just go and replace one cell phone number with the other and it stays on the same page.
Yes.
If they add a second house or a second address, there may not be enough room on that page and it might spill over. And of course, if it's a friend of mine who's a friend who's a girl who gets married, her name changes, that might mean, well, the thing I've ordered it in has changed, so I might have to move her to
exactly.
Okay.
Exactly. And then if we're issuing a delete operation, so basically we're going to flag the data as unused, so it's a less expensive operation. And then finally, select. So queries relating to the clustering key, so this is the order of the data that we're doing. So we can have a seek, and we can have a scan. So there are two types of operations on indexes, the seeks and scans, and we'll look a bit more at those when we come to the demos.
Okay, good to know.
Which is now, actually.
Oh, speaking of which, yeah, there we go.
Great. Okay, so first of all, I'm just going to use TempDB as a store rather than temporary tables. So I'm going to create a table. So we've been through this in the first module, how to create a table, called phone log, which I've just created. Yep. And what we're going to do is have a look at the execution plan. So I'm going to use this button up here to include the actual execution plan.
Okay.
Because I want to show you this tab here. We have a table scan.
So this is how SQL Server's optimizer has decided that's the best way for me to get there.
Yes.
Right, okay.
And it's not so much the best way as the only way, because what we've defined here, we don't have a primary key, we haven't created an index, so therefore what we've created is a heap.
Yeah. Okay.
And how SQL Server accesses a heap is as a table scan. Because it's unordered data, there's nothing else it can do but start at the top and read through till it finds what you're looking for. So I'll drop that table. Now I'm going to create the same table, but this time with a primary key specified.
Okay.
And as I've just mentioned, when you specify a primary key, in order to enforce that primary key, it creates a clustered index.
Okay.
And this, because the table construct has changed from a heap to clustered index, we'll have a look at the difference that makes in the execution plan. So you see now we have a clustered index scan. So if you're ever looking in an execution plan and you see table scan, you know automatically that's a heap, because if there was a clustered index on it, it would be a clustered index scan.
I guess it's worth pointing out at this point that the clustered index was created because you specified one column as a primary key.
Correct.
Now, if I wanted to have a clustered index on a column that isn't the primary key, when I define the primary key, I'd have to explicitly say I want a non-clustered primary key.
Exactly, and then you would create a specific cluster.
Because we can only have one clustered index.
Exactly.
Yeah, okay.
So we can have a look in sysindexes here. So we can see the index has been aligned. So the same we look at foreign keys in the previous module, it's automatically generated a clustered index based on a primary key with a funny name.
Okay.
And it's also listed as a constraint.
So that constraint, there's a relationship between the fact it's a primary key and it has an associated index. That's what makes it a primary key.
Yes, yeah, exactly. So within that demo, so what we've seen here is the difference between a heap and a clustered index. Is a very kind of light intro into it.
Okay.
If we switch back to the slides now,
okay,
and hopefully it'll all start coming together nicely. So the next thing that I wanted to talk about is non-clustered indexes.
Okay.
So we talked about a table structured as a heap or a clustered index.
Right.
So it's one or the other, it has to be one or the other. And a heap within SQL Server is referenced as an index ID of 0, and a clustered index has an index ID of 1. So if you're looking through sys.indexes view we just had a little look at in the demo, and you see an index ID of 1, you know that that's automatically a clustered index.
Okay.
But we don't, just because we can only have one clustered index, we've now got this concept of non-clustered indexes, which we can have a lot more of. So we can have these additional indexes called non-clustered indexes, which will have an index ID of 2 and greater. They're separate objects to the table, where a clustered index is essentially the physical ordering of the table itself. The non-clustered index is a separate object to the table, so the data within the non-clustered index will be copied out and stored separately.
And I know it's just worth pointing this out. I've taught a lot of students who find this concept quite confusing. To a certain extent, a table is either a heap or a clustered index. I know we talk about creating an index on a table, but when you create a clustered index, really that then defines how that table is stored. So a table can be either a heap or it can be a clustered index, but then we can create additional non-clustered indexes on the same table. And quite often you'll hear people talking about querying a heap or querying a clustered index. Really what they're saying is querying that table that happens to be physically implemented as either a clustered index or a heap. So just can be a little confusing.
So, and where we talked about the concept of a clustered index, the analogy of the contents page of a book, if we take that analogy further, a non-clustered index is very similar to the index at the back of a book. So where if you wanted to know everything in a SQL Server book around indexing, you may look in the contents page for the indexing chapter, and then you would read from there. But if you wanted specifically to read about non-clustered indexes, you may flick to the back of the book, and in the back of the book it will have non-clustered indexes, and then it will have the page number for you to find the rest of that information. And that is the equivalent of this last bullet here, where the leaf level contains a pointer to the table where the rest of the columns can be found. So this is the page in the back of the book where you can find the rest of the information that you're looking for.
Okay.
So this next slide is whether the underlying table structure is a heap or a clustered index subtly changes the architecture of non-clustered indexes. So in this example of a non-clustered index on a heap, this going back to that analogy of a book again, the index at the back of the book where we find the word that we're looking for and the page where we can find the rest of the information, that page number is what we call a row identifier, or a RID is how we reference rows in a heap. So in this diagram, the leaf node of the non-clustered index will contain a RID which points to a specific row on a heap.
So that's pointing me down, effectively in the non-clustered index, it's pointing me directly to that's where that row that you're looking for is physically stored.
Exactly.
Okay.
So where you can find the rest of the information. So where we have a non-clustered index on top of a clustered index, because the table structure itself is different, this row where we had this RID or this row identifier which sends us directly to the heap, when we have a clustered index underneath the structure, what we have at the leaf level of the non-clustered index is the clustered index key. So and then we'll go down, we're traversing the non-clustered index to find the clustered index key, and then we're going to go directly to the clustered index to find the rest of the information that we're looking for.
So just to kind of bring that into an example context, I guess if you have a table that has, let's say, a table of customers. So we have a customer ID, and perhaps we have a clustered index on the ID. So that's the order that the data is physically stored in. I may have a non-clustered index on last name. So what I'll do is look up the non-clustered index to find last name Malcolm.
Yeah.
That then points me to the clustered index page where
you can get the rest of the data.
I can get the rest of the data.
Select statement. Yeah.
Okay.
So So the next part is around covering indexes, and this is all related, and we should bring this together in the demo and right after this slide. So a covering index is an index that provides all of the data without having to go down to the underlying table structure. So we're talking about non-clustered indexes and clustered indexes here. So in Malcolm's example of customer ID, if I did a select first name and last name where last name equals Malcolm, then the way that SQL Server would deal with that is to first of all have a look for a non-clustered index on surname, and we'll get down to, right, we've got the surname of Malcolm, and then we've got this clustered index key, so we're going to go to the clustered index to get the first name column because it's not a part of the index.
Okay.
So if we had an index on last name and first name, it's what we would call a covering index, and this is how we would remove these lookups into the underlying table structure. Historically, we'd have quite wide indexes, but with 2005, we had this include option, which is really quite powerful for removing these lookups without the overhead of having a very wide index key.
So to be, again, just to be clear, the kind of older approach, if you like, the only option we had before 2005 was the index then has to include multiple columns in the index itself. So I'm indexing on first and last name. Whereas the include clause lets me say, well, look, the index, the pages in the index where I'm storing the index value, it's just the first name. That's the only thing I'm indexing on. But when I get to the leaf node of that, include the last name.
Exactly.
So I then don't do the additional lookup to go and find that.
So we're copying the data, but we don't have the overhead of also sorting it by last name if we'd included it in the index key.
Okay.
So let's have a look at a demo of that now. So in this demo, I'm going to start off creating a table called book with a primary key. Then I'm going to create a non-clustered index. So notice the syntax here. So create non-clustered index. I'm going to call it IX book publisher, and I'm going to include publisher ID and the release date in descending order.
Okay.
Then I've got a query here to select a few columns from the book table where the release date is less than a year.
Less than a year ago, okay.
Less than a year ago. And I'm going to order it by publisher ID and release date. But before I execute that, what I wanted to show you was this estimated execution plan.
Okay.
So if we have a look at this execution plan, so this is how SQL Server will probably execute this based on the code that you've written.
Okay.
So we're going to do an index scan here, so non-clustered index. If we can have a look, we've got the output list from this index is the ISBN and the publisher ID. ISBN, release date, and publisher ID.
Okay.
Because we have a primary key on ISBN, which has created a clustered index on ISBN.
Okay.
And what I'm asking for is publisher ID, title ID, and release date. So within this non-clustered index key on publisher ID and release date,
Yeah.
I have those values at the leaf level of the non-clustered index.
So I've got the ISBN in the clustered index, and I've got the release date and the publisher ID in the non-clustered index.
Yeah.
Okay.
So this primary key, so the clustered index key, exists in all non-clustered indexes. So if I'm asking for the ISBN and what do we have here? The publisher ID and release date, that would be a covering index.
Okay.
but because I'm asking for the title as well, I don't have that within the non-clustered index.
Right.
So what I'm going to have to do is to take this clustered index key, so the ISBN number, and I'm going to have to look it up on the clustered index.
So I get it from the leaf page of the non-clustered index, because that's ultimately what you find with a non-clustered index, is the clustering key, if there's a clustered index.
Yeah.
And then I'm going and looking up through the clustered index to get the title.
Correct.
Gotcha.
Yeah. So I've got 2 out of 3 of the columns, the data columns that I need, and in order to get the title, I'm going to use the ISBN number to go and look up, and we can see at the bottom here the output list from this key lookup is the title column.
Right.
So we have this index scan, then we've got a nested loop, because we're going to do a key lookup into the clustered index in order to fulfill this query.
And it's a loop because it's doing it for each key that it finds, because there might be multiple books that are published. Yeah.
Exactly. So, and this is fine and it works, and you know there's a 50% cost associated with both of these events, and that's how SQL Server worked basically. But whenever we see key lookups, we're trying to remove them because they're quite expensive, and we've always got this trade-off of removing the key lookup versus having a wide clustered index. But in an example like this, we don't have to, because what I can do is create a new index on publisher ID and release date descending. So I've got the same cost because
index, yeah.
I'm ordering by the same things, but this time I'm going to include the title column within this index. So when we get to the leaf level of the non-clustered index, and the optimizer will say, now I need to go and find title from clustered index. Oh no, I don't, because it's already included in the bottom here. I'll just take this value and I'm complete.
So the leaf level, then again, just to make sure we're clear on this, the leaf level of that non-clustered index is going to include the publisher ID and the release date. They're included on all of the pages in that non-clustered index, because that's what we're indexing on. When I get to the leaf, the thing I'm ultimately trying to find that I'm looking up, it's going to have ISBN because that's the key from the clustered index, and that's what's used to go and look up that. But now I'm also going to include the title down there as well. So I'm shortcutting any need to go any further, because everything I need is actually at the leaf level of the non-clustered index.
Yeah, exactly. And it's quite lightweight. The only overhead really is the additional storage space, but it's much better that that's the only overhead, rather than you're actually sorting by in order to have a covering index before, you had to have it as part of the index, even if you weren't worried about the order in which it was stored. So it's a great way of having that additional data just sat at the end of the index for you.
And when you say store, we're talking about the index pages, not the data pages for the table, but the pages that store the data for the non-clustered index.
Yeah, because the non-clustered index is a separate object, separate from the table itself.
Okay.
So I'm going to run the exact same query again, or I'm going to have a look at the execution plan for it, and you can see now that we have an index scan without the lookup. And the output list from this is the ISBN, because that's the primary key for the clustered index anyway, but we don't need to use that to do a lookup, because we've got the title, the release date and the publisher ID all sat within that non-clustered index key. So we don't need to go to the underlying table structure to provide the data for that query.
So I guess one of the things this is kind of driving home for me is, if you're implementing a database, you to get this right, you've got to have a good idea what are the kinds of queries that I'm going to have. What are the most commonly filtered on columns going to be, because those are the ones that I'm going to be concerned about including in indexes. Yeah,
it's always a trade-off, and you can find, if you're inheriting a database, that there's always a trade-off between too many indexes and too few indexes. So there's an art to finding the right balance between too many indexes, too many include columns. You could be tempted to create an index and include all the columns, but then you're effectively reduplicating the whole table structure itself. So there's a fine balance between.
And of course, every time you insert or update, you're going to have to move everything around to accommodate it. So
yeah, exactly.
Okay.
So if we just have a look at finally we just have a look at the AdventureWorks database here. we have a look at index columns within AdventureWorks. So you can see we've actually got a column here called isIncluded column.
Right.
So within the index columns, we can see whether it's been included or not.
I see. Okay.
So we can combine several of these system views to locate any included columns within the database. So within AdventureWorks, we weren't using AdventureWorks during that previous part of the demo. So this is me running the query against a different database, and it's showing me here that I have 2 indexes with included columns. So this first one here is a clustered index, so of course it's going to be included. Mm-hmm. But this second one here, the column name of comments, is an included column within this product review, product ID column.
Oh, okay.
And you don't need to remember, I mean, who's going to remember that query? You can also view this through Object Explorer. So let's have a look. We have a look at the production product review table. Under indexes, I can double click this and have a look here, and we can see this included columns tab here, so I can view the same information through the UI.
And of course you can create and manage them through the UI.
Exactly,
as well.
exactly.
Yeah. Brilliant, okay.
Great.
Well, let's go back to the slides. So we looked at some system views there. I'm guessing there are other ways that I want to manage the indexes and see what's going on with them. Can you talk me through some of the DMVs?
Yeah, absolutely. So these are really important for everyday use as well as for the context of the exam, is to understand some of these key DMVs. So this first one here is DMDB index physical stats. So this will show you details around the size of the index and the fragmentation statistics. So when we talk about index maintenance later on, we will use this DMV to have a look at the fragmentation levels for an index. And fragmentation occurs as we're doing updates and inserts, and we talked about how those, how we were managing those rows in the clustered index earlier in the module.
Okay.
And the next one is operational stats. So this is going to provide us with index and table I/O statistics. So how the volume of reads and writes happening on this table. And index usage stats is around usage statistics by access type. So when we have a look at the demo shortly, we'll see this kind of breakdown of these types of DMVs and where we can use that effectively for managing an environment.
Okay. Well, and now's your chance. Let's switch back to the demo machine.
Okay, so we'll start off by resetting our demo environment, create a new database. I'm going to create a copy of the phone log table that we've been using previously. I'm going to add a non-clustered index to this for reporting later on.
And of course there'll be a clustered index because there's a primary key that...
Exactly,
yeah. Okay.
Exactly. And then we're just going to insert some data into the table. So the contents of this query isn't important, it's just the fact that I'm pushing a load of data into the table.
Okay.
Then we're going to be using this DMDB index physical stats DMV. It's actually a dynamic management function to return details around the physical statistics. So you'll notice that we've actually got 2 entries for...
Yeah, I was going to say, I thought you said earlier I can only have 1 clustered index.
I did.
Okay.
So because of the way that the indexes work, remember we talked about root pages and intermediate pages and leaf level pages. Okay. So what we have within this clustered index here is an index level of 0, which is the leaf level pages, and index level 1 is actually the root page. So the highest index level is the root page.
So it's showing me the fragmentation, not just for the index as a whole, but for each individual level of the
Correct,
index. Okay.
Yeah. But most of the time what we're interested in is the leaf level fragmentation. So in this example, we have an average fragmentation of 7% at the leaf level of the clustered index, and a fragmentation of 21% on the non-clustered index that I created.
So what does that mean when you say it's fragmented? What?
So essentially it's, remember when we looked at the clustered index and we talked about these inserts and update operations that you do, when you have to everything's in perfect order, and then you need to insert data halfway up.
Sure.
We need to do this page splits.
So we're back to my McDonald's page being full.
Exactly,
right,
exactly.
Okay.
So what you end up with is this kind of C page 47 to carry on and then get back there. So you end up
so
with a lot of...
follow the leader to find the page.
Yeah,
right.
exactly. So this is the kind of fragmentation that we're talking about here. And the other point of interest is the page count, first of all. So a page within SQL Server is the storage unit within SQL Server, which is 8K. And we have an average page space used in percent. So it's 99% used. So what that's telling me is my pages are pretty well full. So I don't really have much fragmentation here. So I'm not too worried about this.
Okay.
And again, for the non-costed index, I've got a low percentage there, but the pages are, I've got a relatively high, actually, fragmentation considering the work that we've done, but the average page space used in percent is quite high. Okay. So I'm not overly worried about this. So what I'm going to do here is do some modification so that this is going to shuffle the data around.
Okay.
And hopefully generate some fragmentation.
So this is me updating my address book, changing people's telephone numbers or adding addresses or whatever it might be. Yeah.
There's been a mass migration of people in your address book.
People who know me constantly move without telling me where they've moved to. I can't understand why.
So we'll have a look at this D&V again, and what you'll see is for this leaf level page, we've now got fragmentation of 90%. So we've got 65% full for a page.
Oh, and many more pages as well.
Yes, exactly. So we've done some inserts, we've done some updates, we've got lots of splits. So the storage required for this this table is larger than it could be because we're 65% space efficient, effectively.
Okay.
So we're going to deal with how to remove that fragmentation in the next demo. But the next thing that I wanted to talk about was, remember this index operational stats that I mentioned on the last slide. So this provides you information around the usage. So this is a raw view of this data here. So what it is giving us here is inserts, so leaf insert counts, leaf deletes, and leaf updates. So this is the index being maintained.
So this is effectively a log of the things that have happened to affect that index.
Yeah, so it's how the index is being used. And if we have a look over here, somewhere we've got singleton lookups and range scans. So if you think about the purpose of an index is to increase the performance of accessing data within the underlying table effectively. So if an index it exists to be read from, but in order to maintain the right view of the underlying data, it needs to be updated. But whenever we're updating an index, it's kind of overhead in order to provide a later view presented by the index.
Okay.
So, bearing that in mind, I put together this query, which looks a bit complicated, but we'll supply the demo scripts afterwards as well. So essentially what I'm doing is taking these scans and lookups, so these are the reads, and I'm looking at the inserts, updates, and deletes, so these are the writes. And I'm joining that to get the index names and ordering it a certain way. And what this is giving me is essentially a list of indexes within this database ordered by reads ascending and writes descending. We think about, as I mentioned, the purpose of an index is to be read from. So what could you tell me about IX log recorded, Graham?
I'd say it's not been particularly useful. We're not reading it, but we do seem to be writing to it a lot.
Exactly. So what we're essentially doing here is that we're making changes to the underlying table structure, which is forcing us to keep this index updated, but it's not actually being read from, which means it's not being used. So it only exists to be read from to improve the performance of reads. So we would use this script when reviewing a database and overhead to look for unused indexes.
Oh, okay, that's useful.
So it's a great use for this index operational stats DMV. So this guy would be a candidate for removal. It's not quite as straightforward as it's not been used ever, because this information will be reset when you restart SQL Server.
Okay.
And it will also be reset when you do index maintenance as well, unfortunately.
Okay.
So, and if you're doing index maintenance on a daily basis, as many people would do, this information will be reset and go to 0. So it's a candidate for, I'm going to look at IX log recorded to clarify whether or not it's used anywhere.
It's a flag, really, is what we're saying. Exactly, it's a red flag. Exactly. I mean, I guess we could have a scenario where once a month we have an absolutely critical report that runs that does use that index.
Exactly.
But for, ever since we last restarted or we last updated the indexes, it hasn't been used.
Yeah.
Okay.
But it's a really useful scenario. So if you inherit a database, for example, and there's 12, 13, 14, 15 indexes on it, and without looking at something like this, you're not really going to know if it's used. So what we would do is try and capture this kind of information on a regular basis, and then over time we can see that it actually hasn't been used for months. Okay. So it's safe to delete.
Right, great. And as you said, we are going to make the scripts available with the course. Of
Absolutely.
If you want to download this at home and play around with looking at your indexes, then by all means you can do that.
So there's one more thing that I wanted to mention before we come off this demo, and that's around unique constraints. So if this IX log recorded, while it's been logged as 0 reads, if it was a unique index, SQL Server would use the fact that it existed in order to help the optimizer, because the fact that a unique index exists means that the data is unique. Therefore, I don't need to read the index to find that out. So there's a little bit of a caveat in there.
So just the very fact that there is a unique index means, hey, we know there's only one of these things.
Exactly.
Right, okay.
I don't need to read it to find out, because the fact that it exists is there. So something to bear in mind that if you are looking at unused indexes, that it's even harder to clarify that it's unused if it's unique.
Okay, right, good tip. Excellent. Let's switch back to the slides. We've seen a little bit about how to maintain indexes. We've seen a little bit about creating them and using include columns. What about this idea of filtered indexes? Talk to me about that.
So a filtered index is a really great feature whereby you can actually add a predicate to your index creation statement. So effectively you're adding a where clause to your index statement. And this example that we have on the right here, where we're creating a non-clustered index on address, but we're actually specifying only where the city is New York. So if I was only interested in employees in New York, then I'd have a much smaller index, because I effectively filtered it by using a where clause.
So the index only includes records where the city is New York.
Exactly.
The other ones are, so what I've got is a sort of hybrid between a heap, if this were it's a non-clustered index in this case.
Yeah.
Can I have a filtered clustered index?
Well, I mean, because the clustered index is the data itself, so you couldn't, creating a filtered clustered index would be deleting the rows in the table effectively.
Right, so this is really a non-clustered thing.
So it's just for non-clustered indexes, yeah.
Okay.
But if you think of examples where you've got a very big orders table, but you're only really interested in yesterday's orders, you could create a filtered index based on time. So you're just maintaining this index for a very small amount of data.
Okay. And I guess, we've listed the benefits there on the slide, I guess. Do you want to talk me through those?
Sure. So it's a faster response time. You think if you've got 1 million rows in a table, but you're only interested in the top 100, so you could create a filtered index which included those top 100, so that's less to store, because non-clustered indexes, remember, are separate objects from the clustered index or from the underlying table structure itself, which means it's going to be faster to traverse that index because it's much smaller and it has a smaller storage requirement, and it's going to be faster to rebuild as well, because you've only got a very small subset.
So if I'm trying to get rid of the fragmentation, it's only that one subset of the index that needs to rebuild.
Exactly,
okay.
Exactly. And it shares some similarities with indexed views as well, in the fact that, remember, we could create a view which gave me a subset of data, and then I could create an index on that view to persist it down. So the filtered index is a much cheaper way of achieving what we would have done with an index view.
Okay, great. So I mentioned fragmentation, and we've talked about it a few times. Let's drill into that a little bit more.
Yeah, absolutely. So fragmentation occurs when data changes. Data changes cause pages to split. So we've, as you said, we've touched on this a number of times, where we've got data in perfect amount of order, and we need to insert something in the middle, and it causes this page to split. Mm-hmm. So there's two types of fragmentation that we often talk about. So the first is internal fragmentation, so where the pages aren't full, and we saw that example of 65% full average page size. And we also have this external fragmentation when pages are not in the right logical sequence, so the kind of the physical ordering on disk is the way to think of that. And that's where we have these references to the next page is
so it kind of spills over onto we've run out of space on the actual page where this index is, so we're going to reference you off to in my address book. It might be sticky notes I've added to the back.
Yeah, so we're splitting a page, but there's no room to put that new page physically next to the first page, so it's now at the end of the data file, and we've got this kind of traversing around the data file to meet that requirement.
All right.
So detecting fragmentation we've seen in the demo. So we have you can have a look at index properties in SQL Server Management Studio. It's not very common to do it this way because it's actually quite an expensive operation. Mm-hmm. And with the overhead of SQL Server Management Studio, if you've got big tables and big indexes, it can take quite a long time to get that information out. So we would most often use DMDB for index physical stats, which we saw in the previous demo. So for fill factor and pad index, so these are two concepts that you need to be familiar with, both in your everyday use of indexes and maintenance, but also for the purposes of the exam. And this is basically saying, for fill factor, what I'm saying is I know that I'm going to need to insert my address book for all my Scottish friends. I know that I'm going to insert more M's at some point. Mm-hmm. So I'm deliberately not going to fill every page. I'm going to leave blank spaces within my page. Okay. So what we're effectively saying is, when I build this index, I'm going to fill the pages to 60% full, 70% full, because I want to be able to insert new rows in those pages to try and avoid page splits.
And this is with fill factor, this is specifically the leaf level pages. We talked about these multiple levels, and this is where the actual data, or in the case of a non-clustered index, the reference to the clustered index is stored. I want to leave space there.
Exactly. So it's the leaf level, and this is the most used area. I'll explain pad index in a second. Mm-hmm. But fill factor, people will often have a generic best practice. If we have an example here of fill factor of 70, but we've got this trade-off of, yes, that would prevent page splits, but what you're telling SQL Server is not to optimize the storage space. Mm. So you've got this trade-off of optimal storage space and performance versus page split. So you really need to know that you're going to get page splits to try and avoid them by using fill factor.
Otherwise, you've got a larger database taking up more space on disk, and all the things that go along with that, the maintenance overhead of that. Yeah.
So one of the things that we would do to fix index fragmentation is to fill the pages properly so we can read more from a single read. Mm-hmm. And what you're doing with fill factor is say, don't store it efficiently, leave gaps in order for me to insert later rows. So it's not sufficient to have a generic best practice generally to say every index should have a fill factor of 60, 70, 80.
Otherwise it just would. That's how the system would work.
Yeah, exactly. Yeah. So certainly on most of the environments that I work in, we would have a fill factor of 100. So if you set a fill factor of 100 or 0, it basically means the same thing, which means fill the pages completely. And then we'd have more regular index maintenance.
And pad index?
And pad index. So pad index is basically the same as fill factor, but it's for the non-leaf level pages. And it will use, so you need to use fill factor and pad index together. So if you're experiencing or you're expecting page splits at the non-leaf level, so on your index keys, that's where you would use pad index to create gaps to avoid page splits there.
Okay. So let's just assume that I've managed to specify whatever fill factor is appropriate for my database. I'm still at some point going to get some fragmentation. I mean, inevitably, databases are things you add data to and you update. So some fragmentation occurs. What do I do about it?
So the first thing that you can do is rebuild. That's the first one that I'm going to talk about, and this effectively rebuilds the whole index. And this is the equivalent of creating the index from scratch, really. Things to bear in mind for this is that it needs free space in the database, so it's going to use some disk space to do a rebuild. But the main point that you need to remember from this is that it performs as a single transaction. So if you've got a very large index and you do a rebuild, some of the environments that we support, it can take 8, 10, 12 hours to rebuild an index because it's so large. If that fails 10 hours in, it's then going to roll back everything that it did. So it runs as an atomic transaction, this single transaction.
Okay.
So we need to be aware of transaction log space requirements when doing rebuilds.
All right. And then the other option?
So the other option is what we call a reorganize. And you can think of this as a defragment. So in the old world, it would have been an index defrag in older versions of SQL Server. So it's what we call a reorganize now. So this will sort the pages, and it does a similar job to rebuild. But the key thing here is that it's always an online operation. So I didn't mention before that an index rebuild by default will take the index offline. So if that's the clustered index and the table is
Takes
offline,
the table offline,
effectively. Whereas a reorganize is always an online operation. It uses less transaction log space because it's not run as this single atomic transaction. So if the reorganize fails or you stop it, you still get all the benefits of what you've reorganized up until that point.
Just a bit like running good old disk defrag. You could stop it at any point, and it defragmented part of your disk, but maybe not all of it.
Yeah. Okay. So we've had some scenarios in the past where we've had customers that would have a 10 terabyte clustered index table. With 99% fragmentation. They don't have the disk space to do a rebuild, but what they can do is a reorganize for a couple of hours a night over a period of a few weeks to try and catch up enough to rebuild the index and then do regular maintenance.
Right. And that will give them the benefits of defragging it a piece at a time, if you like.
Yeah. Exactly.
Okay.
Exactly. So the other part to mention, so I mentioned rebuilding an index is an offline operation. And then we had this online index operations, which is a feature that came out in SQL 2005, I believe it was, where in the enterprise edition of SQL Server, you can specify an index to be rebuilt as an online operation. Which means that it's an availability technology, so we can keep the underlying table running, so we can have multiple users still using the database, so the concurrent user access. It's slower than the equivalent offline operation, because effectively what happens is that SQL Server will create a new version of the index and will rebuild that in the background, and then when it's finished it will switch the pointers over to the new index.
Okay.
So we've got bigger space requirements. It's slower than the equivalent offline operation. But we need to bear in mind this space consideration because we're effectively duplicating the database.
Oh, okay.
It also it enables you to rebuild an index online by using row versioning. Row versioning is supported by TempDB, so it can also cause a knock-on effect of TempDB space as well.
Okay.
So it's a great feature that's enterprise only, but it has a lot of overheads associated to it.
All right, great. So you've mentioned statistics a couple of times. I guess this is the missing piece of the puzzle now.
Yes,
Let's put that in.
So statistics are, again, they're separate objects. They're used by the optimizer to guess or to get a very good estimate of how many rows are going to be returned by an operation. So if you did a select first name, last name from employees, the only way that the optimizer is going to know how many rows are going to be returned is to actually run it. And if you've run it, then you've got the data, so you don't need the most efficient way to do it. So to get around this problem, SQL Server maintains a set of statistics, and the statistics store distribution details of the data within the table. So this example here, I'm using DBCC show statistics to show me the statistics for a last name column. And you can see at the bottom here, I have this range high key, range rows, EQ rows. So this range high key is basically what the optimizer has determined are range high keys in this histogram of the distribution of data. So let me explain how it works. It will make it a bit easier. So if we take a value of Abbott there as a surname, so I can see from this there are 200 rows that equal Abbott. Okay. And then for the surname of Adkins, there are 1,029 rows. So this is equality.
Right.
And between the values of Abbott and Adkins, I have 404 rows. There are two distinct values. Therefore, I'll have an average of 201.
Abby or whatever.
Yeah, exactly. So if I had a value of Abby or Acorn, then the optimizer would estimate that it's either going to be none or it's going to be 200. So I'll assume it's 200, and I'll base all of my my estimations and my execution plan based on those results.
And this is going to do things like help the optimizer decide if there's a whole bunch of discrete values in there and I'm searching for an individual value, then I'm probably going to want to use an index. If there's only two discrete values in there, I might as well just scan all the pages in there. It's just going to be quicker than looking up the index. Yeah.
If I'm expecting 100,000 rows from a 110,000 row table, I'm just going to scan the table.
Yeah.
And that's what you're helping the optimizer to do.
Okay. So I guess keeping those up to date is important then, but otherwise the optimizer is going to start making their own decisions.
Exactly. So as the data changes, we need to keep these statistics updated, and they're updated automatically by default. There's a flag on the database for auto-update stats.
Okay.
We can also do that on demand. So we have this auto-update statistics on by default, which is a database property. We can also issue an update statistics manually. So quite often what you'll find is under a performance problem scenario, this query is not running very fast anymore. One of the things you might do is to go and update the statistics to say, let's take another cut of the distribution of the data to try and help the optimizer have better guesses about what's going on.
Okay.
We've also got SP update stats, so this will update all the statistics in a database, whereas update stats is for specific statistics. And then finally an index rebuild. So the thinking behind this is if I'm rebuilding an index, I'm going to be reading all of the data anyway, so I might as well update the statistics as I'm going along. Because for every index you create, there'll be a set of statistics associated with that index based on the distribution.
Okay. So let's take a look at that then.
Great. So let's have a look at this previous demo, if we've still got the table. So remember in the previous demo, we created this phone log table and we introduced a lot of fragmentation here, and these were the results.
Yep.
So we had this 90% fragmentation, and we've got a 65% average page space used.
Okay.
So now we'll go ahead and remove that fragmentation. So I'm just simply going to do a rebuild of all the indexes on the phone log table. And we'll recheck that. You see, because it's small, it was very quick to go. Average fragmentation is now 0. average space used is 99, and the page count as well is much smaller. So this is now reduced the size because we're far more efficient with how we've stored the data. We're reducing the size of the index.
Less overall pages that are more full now.
Exactly.
All right, so we've maintained some indexes. We've created some, we've maintained them, we've looked at some of the DMVs that we can use to query them. I've just missed out there, we use the covering indexes and the include clause to try and reduce the additional lookup once I've looked through a non-clustered index. Talked about filtered indexes, where in a non-clustered index, I only index certain rows based on...
So I can add a where clause to my index create, yeah.
Exactly. And like I said, we've just looked at the statistics that the optimizer uses to try and figure out, should I use an index, should I scan, what should I do, and then maintaining the indexes. So a lot of information in there about indexes, which I guess reflects how important indexing and index management is when you're implementing a database, or indeed if you're sitting an exam on implementing a database. So a good subject to drill a bit deeper in. Again, we finished the module, go and take a little time, absorb that, have a look in SQL Server books online, particularly at the create index statement and the rebuild and reorganize activities or statements that you can use to update your indexes or to maintain them and remove fragmentation. A lot of that kind of information is critical for not just building a database in the first place, but also for maintaining it and ensuring that it continues to perform to the level that you need it to. So great, we're going to take a little break from there, and we'll come back shortly with the next module, which is...
using store procedures and functions.
Thank goodness you're here to remind me. Using store procedures and functions. Join us after the break for that. Thanks. So welcome back. We've so far in this course looked at tables and all things kind of tabular shaped, and then we looked at indexes and how we can create and maintain our indexes. In this module, what we want to do is to focus on store procedures and functions. So we're getting more into the idea of using the database as a place to implement programming logic and actually build applications. So to talk us through that, once again, we have Christian with us. So I'll hand over to Christian. What are we going to cover in this module?
Perfect, thanks Graham. So first of all, we're going to start by looking at what exactly is a store procedure. So we'll define a store procedure. Then we'll look at a couple of examples of how we can implement store procedures and also parameterize store procedures. So what we mean and what that really looks like. Then we're going to introduce a term called parameter sniffing, which probably sounds a lot more exciting than it actually is, and how that can affect the performance of applications. And it's the cause of a significant number of problems based on the distribution of data. So that will be quite an interesting section to discuss. Then we'll define what a function is, and we'll have a look at scalar functions and table value functions, or TVFs. Okay,
sounds like we've got a lot to cover, so let's crack on. What's a store procedure, Christian?
So first of all, a store procedure, so there are a couple of ways that an application, or if you're interfacing with SQL Server, that you can execute T-SQL code. So the first of all, every statement could be issued by the application. So this is really everything that we've looked at so far. You're sending batches of requests to an application. And the other way is to store groups of these statements together as store procedures. And then we would give that store procedure a name. So these store procedures can have input parameters, which helps with reuse, can have output parameters, and can return sets of rows. And this is really what we're going to look at when we move on to and have a look at these demos.
Okay.
So some of the benefits of store procedures, first of all, it's a security boundary. So users can be given permissions to execute a store procedure without having permissions to the underlying objects.
So if a store procedure queries a table, the person calling the store procedure doesn't need permission on the table?
Correct,
right,
yeah.
Okay.
So as long as the person that owns the store procedure also owns the table.
Right, so that ownership chain has to be intact all the way down. Okay.
It's a way for us to enable modular programming, so it helps us to develop applications against SQL Server and keep them all stored within SQL Server, and they can also improve performance as well. So a single statement issued across the network, so you think an application talking to SQL Server would say execute this store procedure rather than execute this 1,000 lines of code.
So I don't have to hard code a lot of code in my middle tier or my data access tier.
Exactly.
And that has two benefits, I guess. One is it's less fragile because, of course, if the data structures were to change in the database, then the code might break.
Yeah.
And secondly, I'm not sending all of that across to be compiled and run again every time.
Yeah, exactly.
Okay.
And so if we just jump back to the slide there,
sure, yeah.
And we have a better opportunity for execution plan reuse. So we looked at a couple of execution plans in the last section, if you remember. And because the creation of an execution plan by the optimizer can be quite CPU intensive, so we try and reuse these execution plans as much as possible, and using store procedures and parameterized store procedures is a really nice way of reusing those execution plans.
So the optimizer will figure out the best way to execute the store procedure, compile that, and then that stays around in memory rather than having to be redone the next time.
Exactly.
Okay, great.
So here's an example of how we would create a store procedure. So it's just create procedure is the T-SQL that we would use. We're in the sales schema, and this is an example of get salesperson names. And then we have a bit of begin and select. So within here, we've got a select. We're joining two tables together. We're ordering it, and we've also got a predicate in there. So it's a very, very simple select statement that we've wrapped within inside a store procedure.
Okay.
So executing store procedures, we use the execute statement.
Okay.
And we can also use that to execute other objects such as dynamic SQL. And we would normally abbreviate that, as it says there, to exec when we're executing a store procedure. Yeah. So, and again, as we talked about referring to objects before, we would always use two-part naming conventions in terms of the schema and the store procedure as well.
So, exec sales dot get salesperson.
Exactly. Because as we discussed in the previous modules, the name resolution process would go through the default schema. If you had one, if you didn't have one, then it would go to DBO. So there's some extra work for the optimizer to do if you're not specific about the schema that your object is in.
Okay.
And again, exactly the same way of calling the store procedure. Within the store procedure, we need to qualify the object names as well for exactly the same reason as we discussed earlier.
Right, and I guess the other added complexity here, I suppose, is that store procedure may not execute in the security context of the person who called it. It may have its own identity, with its own default schema or whatever. So.
Yeah, exactly. Yeah. So one of the things we do as a best practice then is to have a consistent naming convention and don't use the SP underscore prefix. So SP doesn't stand for store procedure. Think of it like a special procedure. So SP underscore is used for system store procedures. So don't use SP as a prefix when you're creating store procedures.
Yeah, I've seen quite often people use USP for user store procedure rather than a system store procedure.
Yeah, exactly.
Yeah.
And another best practice there about keeping to one procedure for each task. So if you create a single store procedure that has lots of logic and flow within it, it can make it very, very difficult to reuse execution plans. So a common example of that would be if you're on an application or you're on a website and there's lots of tick boxes, and depending on what you tick to what you search for, if that uses the same store procedure, that's going to generate a different execution plan every time it's executed, which makes it difficult to
because
reuse.
You've chosen different options. And,
because you're trying to do too much within a single construct.
Okay. Now, we've seen this before, actually.
We have indeed, yes. So as with when we were creating views, you can also use this with encryption option to protect any IP you may feel that you have around the definition of your store procedure. And again, this is most relevant, or you would most see this within third-party tools that publish part of their code within SQL Server, may choose to use with encryption because they feel like the design is their intellectual property.
But I mean, generally, I guess as it says there, if you're not producing a commercial product, if it's an internal business application you're using, you might be making a rod for your own back for troubleshooting.
It's really, really difficult to troubleshoot if you've got stored procedures and even views that are encrypted, because you can't see the code within it, and if you've lost, the original code, then there isn't anything that you can do about it.
Okay, great. So, time for one of your world famous demos, Christian.
You do flatter me, Graham. Great. So I'm just going to use the AdventureWorks database. Right, let me get back. So use AdventureWorks. So I'm just going to create a store procedure here. So you notice that I'm using create proc just as a shortcut. I'm creating a store procedure called get blue products in the production schema, which is going to select some columns from the product table where the color is blue.
Okay, so a fairly simple, basic example.
So I could run that, but in this case, I'm going to wrap it up as a store procedure.
Okay.
And executing that store procedure is going to give me the same results as if I'd executed the query.
Okay.
Makes sense? So there we've just created a very simple store procedure. I'm going to create another store procedure here called get blue products and models, just to show you here that we've actually got two select statements within this store procedure.
So we've got, I mean, if anybody's got experience with a different programming language, I hesitate to call it a function because that's something else, but if you were creating a method or a block of code that could be called, you can encapsulate a whole bunch of programmatic logic within the one store procedure.
Exactly, right. Exactly. So let's create that store procedure. We've got two select statements here. And the purpose of this is to show you that we can actually return multiple result sets with a single store procedure.
So there's two row sets being returned
Exactly.
from that one thing. Right?
Exactly. But there's actually a mistake in this, in the fact that the purpose of the store procedure is to get blue products and models, but we've actually missed off the where clause for the models.
So when you say a mistake, you mean a deliberate mistake, because we know you don't make mistakes.
Here's one I made earlier.
Right.
So what I'm going to do is, because I've already created the store procedure, I can't create it again, so I'm going to use the alter proc commands to alter an existing store procedure.
Right.
And you'll notice that I've added in my where clause in there to complete the query that I was looking for.
Now we've got the appropriate filter. And it's interesting, the alter proc statement there it's in effect the same syntax other than alter and create. It's identical to the create except for the bit that you fixed.
Exactly.
So really what you're doing is redefining the stored procedure. You're not altering it, just changing a little bit of it, you're redefining what it is.
You're recreating it by using alter, yeah.
Yeah.
And then finally in there at the end it was just we can have a look at all the store procedures within this database by schema. So we can see the two that we created at the end there.
And again, what you're getting out of there by default are the user store procedures. I'm not seeing any system store procedures.
Yes,
there.
that's correct, yeah.
All right, so that's how we implement a store procedure. The ones that you used there were fairly simple. I just wanted the blue product, so I encapsulated that in a store procedure. It's more likely I'd want to have a store procedure where I specify at the time I'm executing it what color I want, and I'm guessing that brings us on to parameters.
That's a really good idea, Graham.
There you go.
So this next slide is about using input parameters. So as Graham said, that we're wanting to get code reuse from using store procedures. And in this case, we're creating a store procedure called orders date status, which has two parameters of due date and status. So parameters have the at prefix. They can also have a default value, as we have here, so tinyint equals 5. And they can be passed, so when we're executing a store procedure, we can specify them in any order by name, or if we list out the values, then we can, as long as they're in the right order, then it'll still execute correctly.
So when I execute it then, I could explicitly say at due date and then give that a value.
Yes.
Or I could just, as long as it knows the first parameter is the due date and the second one is the status, so I could do them by position, but I couldn't mix and match the two.
Exactly.
Okay.
And for output parameters, so you can see in this one we have an input parameter of date time and an order count of output. So we must specify output to create an output parameter when we declare it, and when executing the store procedure.
Right, so it's not just when I define the store procedure, I'm saying this is a parameter, but I'm not expecting it to be passed in. It may be passed in, it may be input and output. But really what I'm going to do is take this value and pass it back to whoever called me.
Exactly.
And when I actually execute it, I specifically state this is an output parameter.
Yeah, and you can see in the diagram the example code there where we're executing get order count by due date, and we're specifying order count as the output there. Right,
and if I were. But just to extend this a little further, because I know some people will be coming from a developer background where perhaps they're used to using C# or whatever to call this kind of code, you would specify in your ADO.NET class that you're building to connect to the database what's the direction of the parameter?
Yes,
is it input
exactly,
or yeah. And back to, let's actually see an example of that.
Okay, let's just make sure that we are in the AdventureWorks database. So now we're going to create another store procedure. Notice that I've used create proc as a shorthand for create procedure. And we've now added this @color input parameter.
Okay.
And where we used to reference blue within the previous example, we've now referenced @color as well. So we're using this input parameter in place of this query.
And the syntax is like a variable, so
exactly.
If I declare it as a variable.
Exactly. So let's create that now. So we execute this store procedure now against red. So now we're able to reuse this store procedure for any color that we wanted.
Very nice.
So in the next example here, we've had a bug report come in saying that people are trying to use this store procedure. They want to use it for products that don't have any color at all. So they're trying to execute this, and we don't have any products. Now, we know that there are products that don't have a color, but we're not returning them at all. And that's because we need to deal with these null values that we talked about in the first session of dealing with nulls.
Because a null can't be compared to another null, because they're both unknown.
Exactly. It's an absence of a value that can't be compared to anything else. So what we're going to do is alter the store procedure because it already exists, and we're going to add some code here to deal with null. So we're going to use isNull to be able to return values that have return rows that have an absence of color.
Okay.
And then we'll test that store procedure again. One for red.
So the red one works, and the null one works.
And the null one works. Let's just be sure about those result sets there.
No, of course, there's actually 4 because each one returns 2. Yep.
There we go. So these are all our null values.
Right.
So that's an example, a very simple example of creating store procedures with input parameters.
Okay, fantastic. So parameter sniffing then.
Yes.
Hardly wait.
So parameter sniffing. So we talked about execution plans and the fact that execution plans can be expensive to create. So if you think you've got a really complicated piece of code that could literally be millions of ways that SQL Server could execute that code. So going through all of that work to find a really good way of executing that, wouldn't it be good if we could reuse that execution plan for subsequent executions?
With the same parameters, presumably.
Yeah, so exactly. So that's what SQL Server tries to do all the time. And then that example that we had about colors, and we added this parameter for red and blue, it's exactly the same execution plan because we've parameterized that code. Okay, which is great. But where we have examples of your data has an uneven distribution of what we call lumpy data. So you've got very few values, the technical term, lumpy data, where you have very few values of some data, but lots and lots of values of another within the same table. So the distribution is uneven, it can cause problems with what we call parameter sniffing. And parameter sniffing is actually this process of executing the store procedure, and we say that SQL Server would sniff the parameter, and then it bases the execution plan on that parameter, and every subsequent execution will be based on that plan.
So the problem we're trying to solve here would be if I had 200,000 products and 50,000 of them were blue, 49,000 of them were red, and one of them was white. Exactly. The execution plan for the white one might be different from if it was blue or red.
Exactly, okay. And depending on who executed it first and which execution plan was cached would depend on whether you got the right execution plan or a very poorly performing execution plan.
Okay.
So options for resolving this. So we could recompile the store procedure every time. So this is a bit of a broad sweep idea for this. So rather than reusing the store procedure, we just recompile it every time. But as much as possible, we want to reuse these execution plans to save on CPU cycles. We could execute the store procedure with recompile. So whenever we call the store procedure, we can also do a with recompile there. So it's very similar to modifying the store procedure itself. And we could also change the store procedure itself within the code that we knew we had a problem with to use this optimize for option hint to tell the optimizer which value to design this execution plan for.
So if I know that 90% of my queries are looking for a color that I've got a good quantity of, then we optimize for one of those, and it should most of the time work out best.
Exactly. Would you like to see a demo of that?
I would love to see a demo of that. Shall we have a look at a demo?
Look. Great. So in this demo, we're going to be using a database called PeoplePS, so parameter sniffing. And within here, I have a store procedure called USP country search. So basically, it's just searching for people within the people table. It's joining to a country table based on country as an input parameter.
Okay.
So it's very, very straightforward. So what I'm want to do is to return the number of people in a specific country. So I'm going to free the procedure cache because I don't want to use, I don't want this plan to be reused for this demo. So we're going to do, have a look at the actual execution plan for this. Let me rearrange my windows slightly here. So this is the execution plan when I'm searching for somebody from the UK. So it's running in parallel. We know this from these little orange disks. The contents of the plan isn't too important. We've got a couple of table scans and we've got a hash match. The way that SQL Server has determined the best way to join the tables together is via this hash join.
Okay.
Then I'm going to free the procedure cache and run the same thing for people from the US. So you notice I've returned a lot fewer results than I had before.
Okay.
So there's about 300,000 people from the UK.
So there's less US-based customers.
Yeah, exactly.
Okay.
And if we have a look at this execution plan, it looks a little bit different. What's important here actually is this nested loop at the end. So a nested loop, SQL Server, the optimizer will use a nested loop where it's got much smaller data sets. So we've got two different plans for two different executions of the same store procedure.
And the optimal one depends on if I'm looking for customers in the US, that's the optimal plan. But if the other one had been executed previously, I might then find myself using the wrong plan.
Yeah, exactly. So, so I'm not going to clear the plan cache now, and I'm going to do a search for people from the UK. So you'll notice that that's worked and it's returned 310,000 rows. If we have a look at the execution plan, we're using a nested loop. We've got big fat pipes traveling between operators here, which is an indication of lots of rows. Mm-hmm. But the interesting point here is to have a look at, we F4 this to look at properties. Mm-hmm. And we have a look at select. We can see this parameter list down here on the right. Mm-hmm. So the parameter is country, but we've actually got a compiled value of US and a runtime value of UK.
So it's optimized the query when it compiled it for US, and we've subsequently executed it with a different value.
Exactly.
Right.
Exactly. So what we're using here is a plan that is inefficient for this value because we've got this lumpy data.
Okay.
Where did we get to? So options to fix it, I mentioned with recompile. So every time we call this store procedure, I could do with recompile. That would get me that execution plan.
Okay.
And US would get me a completely different execution plan. So you notice when I did, I ran dbcc free proc cache, that was clearing everything out of the cache.
Okay.
Whereas with recompile, I'm effectively saying recompile this every time it executes.
Well, and this is when you call it, you're calling it and saying,
yes,
I want you to recompile this.
Yeah,
Okay.
exactly. So we're going to get the right execution plan every time.
Okay.
We could also use statement level recompile, which is quite good. So if you imagine that this store procedure has lots and lots of statements within it, hundreds of lines of code, if I'm using with recompile when I call the store procedure, I'm having to recompile the whole thing every time it executes. Whereas in actual fact, we can use a statement level recompile, which I've got here. So I'm going to change the store procedure to have option recompile. And what this will mean is that every time that batch, so that statement recompiles, every time that statement executes, it will be recompiled without having to recompile the whole store procedure.
So if the store procedure had multiple statements in there, but only one of them was subject to this issue,
yes, exactly,
then that individual part of the store procedure can be
yes,
effectively recompiled. Right.
Yeah, so each statement within the store procedure will have its own execution plan, and we're just recompiling that
Right.
subset. So now we have option recompile. If I run country search UK, I'm getting the right execution plan. So I'm getting the right execution plan for that. And then if I run country search US, I'm getting the right execution plan. So the nested loop is what we're looking for here.
Okay.
And another alternative is to use the optimize for hint. So what I may say is, rather than recompiling that statement every time, I know that while, back to it, here we are, while the consequences for somebody searching for the US and using the plan for the UK plan is minimal, but somebody searching for UK and using the US plan is quite significant.
Okay.
Does that make sense? So what I might say is, regardless of what you search for, I want you to optimize it for a value of UK.
And we'll take a small hit on people searching for the
Exactly,
US.
because people searching for US, there's only 5 rows anyway, so getting a bad plan is an immeasurable execution time difference.
Right.
Whereas the other way around, it would have been quite significant.
Okay.
So if we do free proc cache here and search for US, have a look at the execution plan.
And it's the original one with the...
Yeah, so we can see, even though we've just freed the entire procedure cache, we've compiled it with a value of UK and executed it with a value of US.
Right. Yeah.
Make sense?
Fantastic. Yeah, great.
Good.
Thanks for that. So we've sniffed our parameters. Let's take a look at functions now. So it's something different from stored procedures. We'll have a look at functions.
So let's just clarify, first of all, what is a function. So a function is a routine that's used to encapsulate frequently performed logic. So some of the rules around a function, so it must return a value. There's no execution plan reuse. And there are a couple of types of functions that we're going to be dealing with: scalar functions and table valued functions, which can either be inline or multi-statement.
So, I guess the big difference in my stored procedure here is that rather than encapsulating a reusable chunk of logic that I want to use to perform a particular task, this is something that returns a value. It's really something where I can call it inline, I guess, in some cases, and get back
exactly
a value. Okay.
Yeah. So implementing a scalar function, we have an example here. The thing about a scalar function is that defines a scalar function, it returns a single value, and it will usually include parameters. So we're looking to call a function, we're giving it some data via a parameter, and we're expecting to get something back.
Oh, so in this case, we're passing it in a URL, like you might type in a browser, and it's returning based on the prefix of that URL, whether it's HTTP or HTTPS or whatever it might
exactly,
be.
Yeah.
Okay. All right, well, I guess you better show us one of those.
Yes. So let's just set up a new database in this situation. Now we're going to be creating a function called end of previous month that's going to return a date value. So it's going to be taking a date parameter in, and it's going to be returning a date value. Let's set that up and query the function.
I'm guessing just from the name of that, if I pass in the 5th of February, it will return the 31st of March, which would have been the 30th.
The 31st of January.
February, yes, you're right, previous month, yeah. January.
Yeah. So we have a look at a couple of examples there. So system date time. So here we have, we're in January now, so we've got 31st of December. And if we were looking at something in 2010, we've got 31st of December 2009.
Okay.
And this object property here, we can determine whether the function is deterministic or not. And it's not deterministic because we can't determine the value because we need a parameter coming in, and based on that parameter, it will produce a different result.
So just backing up for a second, because I think this is something that's important, and particularly in the exam, a deterministic function is something where you can predict ahead of time what value you're going to get back. If I have a function that adds two numbers together, if I know what the two numbers going in are, I know what the result's going to be coming back. But if I have a function that returns something like getDate as a system function, well, unless I already know what the data is, then I don't know what the result's going to be coming back.
Exactly.
I can't determine that without executing it.
Yeah,
right.
Exactly.
Okay.
Good. So that was just a very, very simple example of creating and using a scalar function.
Okay. So we talked about scalar functions. You're going to talk to us a little bit about table-valued functions.
Yes. So a table-valued function, or TVF for short, returns a table data type. So rather than returning a value, we're actually returning a table as a data type.
Okay.
So we have two types of table-valued functions. So we have inline TVFs. So that has a single select statement, and then we have multi-statement table-valued functions that will allow you to construct, populate, and then return a table within the function itself. And we can use these to replace views when we need more complex logic to achieve those results.
Okay, so if it was dynamically generating something that was going to end up in a table rather than just querying existing tables, a function's a better way to go than a view.
Exactly, right. Yeah. So a bit more complex logic.
Okay, well, we're switching backward and forward at a rate of knots here, but let's have a quick look at those.
So we're going to use the AdventureWorks database for this one. We're going to create a table-valued function, so we can see it returns table.
So it's specifically in that returns clause that I'm specifying this returns a table rather than an integer or whatever.
Yeah, exactly. So we're returning the result of this select statement. And so we're going to run this table-valued function, and see we're selecting from the table-valued functions, and this is providing for us the last two orders for this specific customer.
Right, so we're passing in the parameter of the customer ID and the number of orders we want, and that's what's being returned.
Yeah, exactly. Okay. So, and then the second part of this I wanted to show you was how you can use this cross-apply to apply the results of this select statement. Right. So we're using cross-apply, so we're going to evaluate this function that we've just created for every row that's returned from the above select statement.
Oh, so I'm using the same function for every row that's returned by the initial select statement. So I should get the last orders for every customer from that select.
Exactly. So let's run that, and there we go. So cross-apply is something that's really useful to be able to evaluate the results where you're expecting multiple rows coming out. So we use it a lot for troubleshooting some of the internal system views as well, and evaluating some of those dynamic management functions that we were reviewing earlier on.
Okay, right, great.
Good.
So that pretty much takes us to the end of that module.
Yes.
And we've looked at two main kind of sections there, I guess. One was store procedures, which are units of reusable programmatic logic to perform a task, and I can pass in parameters and I can get output parameters to return me values. And then I guess if you haven't compared the two before, it can be slightly confusing sometimes. There are store procedures that are functions. Functions are generally things that are used either in line in a piece of code to return a specific value, or to encapsulate something like we saw, to return a table where I pass in parameters rather than query a view.
Yeah.
So there's a fair amount of stuff there to look at. If you're prepping for the exam, then there's a whole bunch of things there that you need to be looking at. Go through the examples that we saw. Again, we'll be including the code as a download from this course, so go through that. But definitely have a look at SQL Server books online, and have a look at the data in there, the information there about implementing store procedures and implementing functions. And in particular, take a look at the difference between the two types of table functions. It can be quite important to be able to distinguish between those.
And as with the other modules, use these topics as marker points in your learning. Everything that you need to learn about these wasn't contained in this module, but they're really important things that you definitely need to be aware of and familiar with for the exam.
Yeah, fantastic. Okay, so hope you've enjoyed that one. Go off and do a little bit more studying on store procedures and functions, and then come back and make sure you join us for the next module, which is all about transactions. Welcome back. So far we've looked at tables, we've looked at indexes, and in Module 3 we looked at store procedures and functions. What we're going to look at now, having taken a little time to learn a little bit about how we can encapsulate programming logic in functions and store procedures, we want to kind of take that to the next level and talk a little bit about how we can use that programming logic to manage transactions and make sure that our data, our modifications to the data is done in a kind of atomic and secure fashion that makes sure all the changes go through. So to talk more about that, Christian is with me again. So Christian, what are we going to cover in this one?
Great, thanks Graham. So first of all, we're going to start off by defining what a transaction is and how we manage and use transactions, because it's really a fundamental concept for how we use SQL Server. Then we're going to have a look at understanding isolation levels, and again, this is another core topic, certainly for your use as you develop against SQL Server, but definitely in the exam. There'll be lots and lots of questions and scenarios that will really lean on your understanding of different isolation levels and what that means. Then we're going to have a look at locking. We're going to have a look at how and why SQL Server uses locking. And then finally, we'll have a look at some locking problem scenarios and discuss what you can do and how you can really troubleshoot that.
All right, sounds good.
So let's start off. So managing transactions. So defining a transaction first. So a transaction is a group of tasks that defines a unit of work. I guess it doesn't really have to be a group of tasks, but the key point here is that it's a unit of work that either must succeed or fail together. So no partial completion is permitted. So individual data modification statements are automatically treated as standalone transactions, and we call these implicit transactions. So if you did a single update statement, that's an implicit transaction in there where it will either succeed or fail. It won't partially complete.
So if I were updating all of the rows in a table where the value was something, it wouldn't get halfway through and update some of them but leave the rest of them as they were. Either they all get updated or
exactly. And you don't need to make it explicit that it's a transaction because it's implicit in what you're trying to do there.
Okay.
And then we have explicit transactions. So you can also control this to define your own transactions. So we can use begin to begin a transaction, commit to finish the transaction and say, I've definitely finished and I want to commit all those changes. Or you might want to say, actually, there were some errors detected there, so I want to roll back those changes as well. And we call those explicit transactions. So implicit and explicit transactions.
Okay. So we've got an example on this slide then of implicit examples. You want to talk us through this?
Yeah, sure. So we've got partial success here, even with its structured exception handling, because this isn't a transaction. So even though we're saying insert into the orders table, insert into the order details table, and if there's an error, send me, raise a flag and send an error number. What we're not saying is, I want you to roll back those changes. So if we had an insert into the order details table that failed, we wouldn't roll back any changes that we'd inserted into the orders table.
So there's actually two transactions going on here. There's two implicit transactions. There's an insert into the sales.orders table where either all of those inserts into that table succeed or they all fail.
Exactly.
But then regardless of whether, well, presumably if they succeed, we then go into the next step and we start to insert order details, and either that all succeeds or fails. But if that fails, it won't roll back the inserts we've already done into the orders table.
Exactly.
Okay.
So then we move into explicitly defining a transaction. So we take that same piece of code and we wrap it in a begin and commit transaction. And because we have this try catch, what we're saying is if an order fails, so that one of these insert fails, then we're going to roll back that transaction. So I want to insert an order with order details or neither.
Right, so in that case, I don't end up with kind of orphaned orders that don't have any matching details. Yeah. We roll the whole thing back if anything goes wrong.
Exactly.
Okay.
Should we have a quick look at that?
Let's look at that.
Okay, so we're going to switch over to use a database called T-SQL. I'll just clean up any of these tables. So we're going to create a table called simple orders, simple order details, just as we've seen in the example slides.
Okay.
So I'm going to execute this try catch to insert two orders with two sets of order details.
Okay.
And I've got a failure there. So I'm conflicted with a foreign key constraint. So we looked at primary keys and foreign key constraints earlier. So that's failed.
And you caught the catch section there, just because we haven't talked about structured exception before. The reason that hasn't shown up as a red error is because we actually caught the error and then handled it. So
yes, yeah,
you've got your own error handling logic there, yeah.
But if we then have a look at orders and order details, we've actually got a partial success. So we've got one order with order details, and we've got a set of order details with no, we've got an order without any order details. Yeah.
Okay. So clearly that's not what we want.
Exactly. So we'll clean up those tables and recreate them again.
And there's nothing different in the definitions of the
table.
Nothing up our sleeves. It's just the same table.
The same. What you see is what you get.
Okay.
So all we're doing now is wrapping a begin transaction and a commit transaction around here. Okay. And if they succeed, then everything will be inserted. Okay. But we've also got this catch here. So if there's an error, we'll roll back both of those changes.
Oh, okay.
So let's run that.
So that one's worked. We've inserted one order and the order detail that goes with it.
Exactly, yeah. So let's delete those rows and execute something with an error. So we've got the same error that we had before.
Caught the error, yeah.
But this time we've got no orders inserted.
So even although the order statement we know would have succeeded, the order detail statement failed, and therefore the whole thing was rolled back. So we don't end up with that orphaned order.
Exactly. And then let's just clean that up for later.
All right, great, thanks. So transactions then clearly a core part of maintaining. If you've got multiple tables and you're inserting into them and you want to maintain that integrity, it's really important to be able to do these with transactions. What if I've got multiple users accessing all of those tables at the same time, or multiple applications accessing? And we've got this concurrency issue. Talk to me a little bit about how I deal with that.
So exactly. So managing concurrency is the ability for multiple processes to access the same data at the same time. So we're talking about lots of users interacting with the same data at the same time. That's what we call concurrency. And there are really two approaches to managing this effectively. So pessimistic is this first approach. So that assumes that lots of different processes are going to try and read and write the same data simultaneously, and uses locks to prevent conflicts. And this is the default and is the kind of the traditional concurrency model for SQL Server, is to use locking based on pessimistic concurrency to remove access to avoid these kind of conflicts.
So I'm pessimistic. I'm assuming that you're going to try and update the table at the same time I'm updating it, or the row at the same time I'm updating it. So I'm going to prevent you from doing that.
Yeah, exactly. And the other approach is optimistic. So optimistic concurrency was introduced in SQL Server 2005. We've got a lot of really good stuff in SQL Server 2005. And optimistic concurrency introduced these snapshot-based isolation levels, which use row versioning rather than locking to manage concurrency. But pessimistic concurrency is the default, and in terms of your learning towards the exam, you need to be very, very familiar with this idea of this pessimistic concurrency approach and how locking works.
Okay, so as it says there, pessimistic is the default.
Yeah.
So what about some of the issues I might face if I'm having to deal with concurrency issues?
Yeah, so we've got a number of concurrency anomalies with lost updates, dirty reads, non-repeatable reads, and phantom rows being inserted. And these are really, we would decide whether or not these types of anomalies were attractive, so they may actually be useful to us, and we would use something called isolation levels to control whether or not we wanted these non-repeatable reads and dirty reads to be introduced into the application.
So can you talk me briefly through each of these things? What for example, is a non-repeatable read, for example?
So a non-repeatable read, for example, is if we had I wanted to say I'm in a shop, just to give a physical example. So I'm in a shop, I'm closing down my shop, I'm going round all the tills, calculating how much each till has taken during the day. And I go to till 1, and that's taken a certain amount. I'll go to till 2, till 3, but the tills are still trading, and by the time I get back to till 1, that value is different. Right. So it's a non-repeatable read. So once I've read it, by the time I read it again, it may have changed.
So in the database world, if I've got two separate applications or users accessing a table, I might read one value and go off to do some additional work, but in the meantime, someone may update that row and change the value that I've originally read.
Yes,
it's a non-repeatable
exactly. And that may or may not be acceptable to you, and you can prevent non-repeatable reads, or you can enable repeatable reads for yourself by changing the isolation level, which will lower your concurrency, so you can keep people out of the data in order to maintain your repeatable read. Right. It may make more sense when we talk about the isolation levels.
Yeah, okay, excellent. Which we're about to do.
Yes, so isolation levels. So the first isolation levels. So we're going from very flexible in terms of concurrency, allowing everybody to access, right the way through to very, very restrictive. So starting off with read uncommitted. So what this means is I'm happy to read data that hasn't been committed. So what we sometimes refer to as dirty data. So if I'm selecting from a table, I want to get rows that may not exist or that may not be valid. So I may get an order details that doesn't have an order as yet, or something that gets rolled back.
Because there's another transaction that's only partially complete at this point.
Yeah. So the benefit of this, if you like, is that it doesn't hold locks when reading data. But the downside is that you're getting this uncommitted data.
Okay.
And the next one is read committed. So read committed is the default isolation for SQL Server. And basically that means that I'm only interested in data that has been committed. Okay. And the way that I will do that is when I'm reading data, I'll take a lock to prevent people updating it.
Okay.
While I'm reading it.
So it's going to allow non-repeatable reads and phantoms. I'm guessing in this instance, so the example would be if I've read the data and before I finish my transaction, another transaction might go in and modify something I've read, but I've already read it. It was committed at the time I read it.
Exactly.
So that's fine. And similarly, I might get all the rows from a table, all the committed rows at the time, but in between times, another transaction might come in and insert a row. So there's a phantom value that's in that table, but I'm not seeing it because I've got the committed values.
Yeah. So people will often use read uncommitted because it doesn't take locks to read data. There's this kind of expectation that it's more performant, which it is, but you're causing lots of problems in the fact that you're not locking data that you're reading. Whereas with read committed, what we're saying is if somebody is writing data, I'm going to wait for them to finish before I read it. So I could be blocked by somebody writing data.
Okay, that makes sense.
Makes sense.
Well, let's move on to the next one, which is repeatable read.
Yep, so repeatable read. So the difference between read committed and repeatable read essentially is under read committed, if we're reading from a table, we will take a shared lock, and we'll talk about locks coming up, in order to read that data, and then we'll drop that shared lock once we've read it. But under repeatable read, what we're saying is, I'm going to read that data, but when I read it again, it needs to not have changed. So I'm going to put a lock on it, and I'm going to hold that lock till I've finished what I'm doing.
So, and if there's another transaction that's ongoing, we avoid that situation with read committed, where I've read all the rows from a table. If I go back and read them again for whatever reason, and in between somebody has tried to insert, they won't have been able to insert because I'll have held a lock on the table.
Exactly. So there's benefits to that in terms of the level of isolation you have for yourself, but you sacrifice concurrency for that.
All right. Well, the next one on our list is serializable. So
yes.
Tell me a little bit about that.
So serializable is effectively, you're effectively saying everything I do, I want to lock everybody else out. So you're serializing access to the data. So it's a very, very restrictive in terms of the isolation that it provides. It makes your transaction very isolated, but it will block everybody out. So we tend not to use it very often in kind of day-to-day operations. We would really use read committed, repeatable read as something that's a bit more loose in how we can flexible in managing concurrency.
Okay, so I guess serializable is, its place would be where there isn't a high likelihood of lots of different concurrent users trying to access the same data, because otherwise I'm just going to have locks that prevent anything getting done.
Yeah.
And I guess the important point at this stage, just to re-emphasize, when we talk about these locks, it's for the duration of the entire transaction, from the point when I first access that piece of data right till the transaction gets committed or rolled back, which is why we're talking about this having talked about transactions. Because while our implicit transactions, individual statements, will hold locks and then release them, by and large, unless we're talking about huge volumes of data, those are over fairly quickly.
Yeah.
But if I'm actually implementing an explicit transaction that does lots of different things, I might actually end up holding lots and lots of locks until I'm ready to commit. So the next one in our list then is snapshot isolation.
Yes, so Snapshot, as I said, is new for since 2005, and Snapshot is the only optimistic isolation we have. So as I mentioned before, it uses row versions rather than locks. So effectively, what happens is when you go to write something, the previous version of that row gets stored in the version store, which is in tempdb, and then if somebody wants to read that committed value, it will be returned from tempdb instead of them being blocked.
So we're not locking them out, we're allowing them access to the previously committed value.
Exactly.
And then when we're finished, our transaction will be committed, and that then becomes the committed value.
Exactly. So we would use snapshot isolation to help us resolve these situations of readers and writers blocking each other, because it allows for much greater concurrency in those kinds of scenarios.
Okay, that makes sense. So let's move on and look at locking. And we've talked about the isolation levels and the fact that they incur locking. I guess we probably need to drill down a little bit and understand how does that locking mechanism work. So let's take a look at that.
Sure. So in terms of understanding locking then, so SQL Server by default uses locks to deliver the level of isolation that you specify. So remember, we are read committed by default. Mm-hmm. So there are two main locking modes that you really need to be familiar with, and that's shared and exclusive, or SH and EX for short, as we'll have a look when we come to the demo.
Okay.
So whenever I read data, I need a shared lock in order to read that data. And a shared lock is compatible with other shared locks, so anybody can read the same data at the same time. So we've got a good concurrency.
Okay.
Now, whenever I want to write data, I need an exclusive lock, because we can't have multiple people writing the same data at the same time.
Okay.
So only one person will get this exclusive lock in order to update the data.
Right. Okay, that makes sense.
But the key point to this is that shared lock and exclusive lock aren't compatible. So if I want to read something that somebody's writing to, I will have to wait until they finish writing.
So if you've already got an exclusive lock on it, you then can't get a shared lock. And if there's already a shared lock on it,
you have to wait for that to drop in order to be able to do your write.
Okay. So what about these other locking modes then?
So there are a couple of other locking modes as well. So we use the update lock. Again, we'll see in the demo, and the main ones are shared and exclusive. So an update lock is taken when a process needs to read data before updating it, and it's involved. It's part of how SQL Server works to help us prevent deadlock. So it's automatic and you wouldn't control this behavior, and we'll see an example of where it fits in. So if you wanted to do an update based on data that you read, you would take an update lock before taking an exclusive lock.
All right, okay, I see.
Okay. And intent locks, so we would have an intent shared, intent exclusive, intent update lock, is basically used to indicate locks that are present at a lower level of granularity. So if I want to read a row, so I'm going to take a shared lock on the row, then I'm going to take an intent shared lock on the page, and I'm going to take an intent shared lock on the table. And that is to prevent somebody coming in and taking a higher level lock. It's like if I wanted to do, and somebody else is coming in and they want to take an exclusive lock on the table. So instead of SQL Server having to go down and see am I free further down to be able to lock this whole table, if there's an intent shared lock at that table level, it's an indicator that there's a lower level lock that's incompatible for the write.
So I've locked this row, so I'm reading it, but chances are I'm going to want to read more than this one row from the table, so I'm intending to lock the rest of the table. Gotcha. Yeah. So what are some of the problems we might hit with locking then?
So blocking locks is the most common kind of discussion point that we have around locking, and we've alluded to that a couple of times around shared locks and exclusive locks. And it's this scenario of I've got lots and lots of users reading catalog data on a website. They're doing lots and lots of searches, but then I want to update something. These read locks are incompatible with exclusive, shared locks are incompatible with exclusive locks. So this combination of read-write activity is what causes these blocking locks. So to define a blocking lock, it's really that processes are waiting for access to resources. It's not wrong, it's how the product works, and whether or not that blocking lock is a problem for you depends on your business logic and your application in your scenario.
So I'm guessing you're building an application where you would have to have either some sort of timeout while you're waiting for the lock, or some sort of retry mechanism that says, well, if you can't access the table, wait for 30 seconds and try again, or whatever it might be.
Yeah, it's a very, very common performance tuning scenario where you have blocking locks, where you're developing on a small database, small data sets, the queries run really, really fast, so nothing's ever a problem. Suddenly you've got a massive data set, and the query that you wrote that was sub-second now takes 10, 20, 30 seconds to complete, but is holding locks during that period and is blocking other processes.
Right. Makes sense.
So we do a lot of kind of troubleshooting around mature applications with varying data sets. Yeah.
So what about deadlocks then? Tell me about that.
So a deadlock is another interesting term, a bit like parameter sniffing. It sounds like
sounds really exciting.
It sounds like a cool term. So a deadlock is basically this principle of two processes each hold a lock that the other one needs to continue. So they're stuck in this deadly embrace of I can't complete because I need to get a lock on this resource, and you can't complete because you need to get on the lock of the resource that I have. And so we've got exactly the same requirements, just the other way around.
Just after you, no, after you, no, after you.
Yes, yeah, exactly. So, and SQL Server will automatically detect and resolve this situation. Because if it didn't, then you'd just be permanently hung. It wouldn't go anywhere. So SQL Server will detect a deadlock, and it will automatically kill the transaction that is the cheapest to roll back.
Right. So there's less work involved in rolling back the transaction.
Exactly. So it may not be immediately apparent to you why it's chosen that specific one, but it's chosen it specifically because it's cheaper to roll back the changes that it had made.
And I'm guessing that the application whose transaction is rolled back then just receives an error, and if this is likely, it's one of the things you should be checking for.
So your application needs to be able to handle deadlocks and to reissue that transaction, right. and everything carries on. So deadlocks themselves aren't necessarily a problem, and lots of applications will infrequently see deadlock events, and as long as the application handles them appropriately, it's not a problem. It's when something changes and you start to get several deadlocks in a kind of frequent time period. Several deadlocks in a day, for example, would be something to investigate. One deadlock every 6 months may not necessarily be an issue for you.
And it might be. I've seen examples in the past where if you've got one stored procedure that updates the customers table and then the, addresses table in that order, it's probably not a good idea to have another stored procedure that does the same updates or updates to the same tables in the opposite order, because then you're increasing the likelihood that one connection will lock one table while the other one locks the other. So exactly.
So there's a development best practice there to do your table updates in the same order
throughout all of your stored procedures.
Your application. Yeah, exactly.
So a couple of trace flags you've got listed here.
Yes, so a trace flag, we haven't mentioned trace flags up to now. So trace flags are a way to enable what were undocumented behaviors in SQL Server, but it's now we would use them to enable extra functionality in the product. And in this case, we've got a trace flag 1204 and 1222 will spit out lots of additional information about what's happened when a deadlock was detected. So what we would typically do is, if you know that you frequently get deadlocks, you'd probably enable these trace flags permanently, so you could analyze the outputs and work out and resolve these deadlocks. And how you would switch that on is by using dbcc trace on. So we've got in this example here 1222, which provides, this is the SQL Server 2005, I think this one was introduced, and it spits out an XML output of the blocking details, and 1204 was an older version of that. And sometimes we'll enable both, and certainly within the context of the exam, you should be aware that they're both deadlock-enabled trace flags. Okay,
and I can turn them on with dbcc trace on.
Yeah.
Are these trace flags I can also configure at the command line when I start the SQL Server service to it?
Yes, yeah, exactly. So if you go into Configuration Manager, you could add a startup parameter of -T and then the trace flag, and then it'll always
start
be there
whenever SQL Server comes up.
Yeah,
okay,
exactly.
Great. All right, so we're going to switch over to a demo, and we'll have a look at how we do this.
Okay, so the first thing we're going to do here is to set the transaction isolation level to repeatable read. So we talked about repeatable read isolation level as allowing you to read the same data twice. and that's different from the default, which is read committed. Shall I just run that? And then we're going to start a transaction. We're going to begin transaction just to select star from the employees table where last name equals Buck. And the reason that I've set it to repeatable read rather than leave it at the default is if I was on read committed, then I would take a shared lock on the row, and as soon as I'd read the data, I would drop that shared lock because it's a non-repeatable read. But because I'm now in a repeatable read isolation level, I'm holding that shared lock for the duration of the transaction. And because I haven't finished the transaction, I'm holding a shared lock, and we can go and have a look at those details.
Okay, and just to clarify, the transaction isolation level that you've set there is for this session. You haven't switched the database into a different mode, it's just for this session.
Yeah, exactly.
Yeah.
So if we have a look at the tranlocks view, so we can see here that we've got, so session 52 is the session that I'm in. Mm-hmm. So we have a key lock here. And what that means is that I've got a shared lock on anyone with the value of Buck on last name, but also any future rows with the value of Buck. So this is why it's a key lock rather than a row lock. I've also got, and remember IS, we talked about intent locks.
Yep.
So I've got an intent shared lock at the page level here. So page 281 in the first data file. I've also got an intent shared lock at the object level, so the table itself, okay. And then I've got a shared lock in the database. So what this means is that anybody that wanted to do a table lock to delete all the rows, for example, wouldn't be able to, because you can't get an exclusive lock when there's an intent shared lock on there. So it's an indicator right. that further down this hierarchy there's a shared lock somewhere.
Right.
Make sense? So let's go to a different window and we'll do an update. So I'm just going to where we have this guy with a surname of Buck, I'm just going to update his title to be Doctor instead of Mr. I'm sure he'll be very pleased about that.
Change the database as well.
Oh yeah. I think we're in T-SQL, aren't we? And I'm going to run that update now. So that update is now executing.
But it's not able to complete because it's waiting on the, yeah, okay.
Yeah, it's waiting on something. So if we have a look, if we have a look at these locks again, so we've now got a number of other locks going on here. Mm. So session 51 is this update that I'm trying to do. So we can see the locks that he's got here. And what's interesting here, so we have a look at this page 281. So it's the same page. So we've got intent exclusive. So he's looking to get an exclusive lock. Right. He has an update lock. So remember we talked about update locks. Mm-hmm. Is a way of, it's a lock that we need to read data before we're updating it. Mm-hmm. And that's compatible with a shared lock, so that's been granted. But what we're looking for here is a conversion to an exclusive lock, because we want to make a write, so we're doing an update.
Okay.
But we're only updating one row, it's still not working, so this is stuck.
Right.
Okay. So then we can have a look at DMV, and we'll talk about towards the end of this in terms of troubleshooting, called DMOS waiting tasks.
All right.
So within that, we can have a look at who is waiting for things. So basically we have a wait type here of a lock, LCK means lock, an exclusive lock. And what I can tell from this is that session ID 51, so we can see is executing, mm-hmm. is waiting for a lock, an exclusive lock, and it's being blocked by session ID 52.
So if I'm troubleshooting blocking, then these DMVs are a great way to get to the bottom of, well, what's blocking what?
Yeah, exactly. Who's waiting for what? So then I can just, if I roll back this transaction, then this update has now
this
completed.
guy's finished, right.
So if I go back and have a look at my locks, we should see, so we've just got shared database locks because I'm using this database in both of these sessions.
Right.
So that's exactly what we were expecting to see. So the next part of this demo I wanted to have a look at was this concept of deadlocks that we mentioned, this deadly embrace. Yeah. So first of all, I'm going to set trace flag 1222 by using dbcc trace on. So this -1 means enable this trace flag for all sessions. So I could enable it just for this session, but force of habit when I'm using trace flag to do it for everything. So I'm also going to set up Profiler. So Profiler is a tool that can be used to have a look at what SQL Server is doing when you execute code. And it's quite a heavyweight tool in itself and is really beyond the scope of the sessions today. But what I wanted to show you in here was this deadlock graph that we'll produce. So I'm setting up this trace to be running, and when we experience a deadlock, we're going to capture some information about that.
Okay.
Okay, so in order to simulate this deadlock, what I'm going to do is set up a new window. There's a specific order of things that we need to do here. I'm going to begin a transaction in session 1 where I'm going to issue an update statement to update Buck to have title of courtesy as doctor. But because I'm not committing the transaction and I'm doing a change, it doesn't matter what isolation level I'm in here because I still need an exclusive lock to do this. Okay. And I'm not going to drop that exclusive lock until I determine whether to commit it or roll it back.
So it's updated that row, but we haven't finished the transaction, so it's still going to hold on.
So it's still holding the lock, right, yeah. Okay. So then switching over to session 2, I'm going to do the same thing for somebody called King.
Okay.
So I do exactly the same thing. Make sure that's working. So if we flicked back and had a look at the locks that were held open, we can see that we have a number of exclusive locks that have been granted against these keys, and they're held because we haven't told SQL Server whether or not to commit them.
So I've got one held by session 51, one held by session 52, and because they're at the key level, we're actually down at those any row with that last name of Buck or King.
Yes, yeah, exactly. So now what I'm going to do is to try and do the same update in session 1 as I'm currently running in session 2.
So you're going to try and access the row that is being updated by the other session.
And this won't work because the other row is already doing this.
Okay.
The other session is already doing this. So that's going to stick there. So
it doesn't fail as such, it's just waiting for the lock.
Yeah, exactly. So it's waiting for the lock. Now if I switch over and in session 2, I'm going to do the same thing as the first statement in session 1.
Okay.
So what I'm creating here is I'm going to update Buck, I'm going to update King, I'm going to update Buck, I'm going to update King. So they're both doing the same thing, just the opposite way around.
Right.
So they're going to be dependent on resources that each other holds locks on.
Okay.
So if I execute this now, it succeeded.
So that one didn't get blocked.
So this one succeeded because if we switch back here, we find that this one was chosen as a deadlock victim.
Right.
So SQL Server has automatically detected a deadlock situation and it's chosen a victim and rolled back the change.
Right. Okay.
Okay. Now if we switch over to, we start a new query and we have a look in the error log. Excuse my typing. have a look at the bottom of the error log here, what you'll find is that we now have this deadlock information. Because of that trace flag 1222, we now have the deadlock information, which gives us the processes involved in the deadlock itself. So we can see that the deadlock victim was running this command.
So I get pretty detailed information about what was going on in this deadlock.
Unfortunately, it's not very easy to consume because it is so detailed.
Yeah.
But it's one of those things that, because it captures so much detail, you know, you're talking about the update locks, exclusive locks, so you can work out exactly what's happening. But a nicer way to view this information is what we've captured in Profiler.
Oh, okay. Pretty pictures, look at that.
Yeah, so within Profiler, we've captured this deadlock graph event of exactly the same thing. And we can see that we have session ID 52 on my left there, and session ID 51 on the right. And we can see the key locks based on the values that we were updating, and we can see the order in which we had update locks here. And we can see the blue cross. If we hover across, we can see that this is the statement that was chosen as the deadlock victim, which means this is the one that succeeded.
Oh, so that's pretty useful troubleshooting information. I guess that's easier to digest than what's in the log file.
Exactly. It's the intention is that it's much quicker, but you also need to bear in mind that Profiler is a client. It's called a client-side tracing, so it's quite a heavyweight tool, albeit not for this.
And I wouldn't want it running all the time just in case.
Yeah, exactly. It's an interactive desktop application, so you wouldn't leave it running there.
All right, great, fantastic. All right, so that's pretty much covered everything we want to cover about transactions and also isolation levels and locking, which are all kind of related to one another.
Yeah.
Transactions, we talked about the idea of implicit transactions. So every statement that modifies data is implicitly a transaction. But if we want to have multiple statements that are executed as a single unit that either all succeeds or fails, what we tend to call an atomic. People talk about ACID. Transactions where it's atomic, consistent, isolated, and durable. So it's then stored on the disk. So if you want to have a transaction that is that atomic unit of work that's all done and then stored, then you have to explicitly create a transaction with begin transaction, commit, and if you find an error, roll back.
Yeah.
And that then made us think about, that's great if I've got one person using the application, but if I've got multiple users at the same time, I want to use isolation levels to determine what can I read that may be in the process of being modified by a transaction. And it's a question of choosing the appropriate isolation level depending on which of those types of anomalies your application can deal with. Can I live with the fact that I read this data, but by the time I do something with it, another transaction may have modified it? Then we talked about locking and how the different types of locks, those shared locks for reading, the exclusive locks for updating, and the other types of locks, update and intent locks that we would use. And finally, how to troubleshoot locking problems, the fact that we have locks that block other processes, and in that deadlock situation where you have this kind of, after you, no after you, no after you type thing, where ultimately two processes are blocking one another, one of them is selected as the victim. And I guess the learning from that is, how do you troubleshoot that? And we can set those trace flags on. And also, how do you deal with that in an application? And fundamentally, it comes down to tracking for that deadlock victim error and retrying or whatever you need to do.
Exactly, yeah.
All right, so I hope you've enjoyed the session on transactions. Again, lots for you to get your teeth in here. If you are preparing for the exam, I do suggest that you read up on the different isolation levels and when they're appropriate, the types of anomalies that are permitted under each of those isolation levels, because that's a really important part of understanding which isolation levels that you need to choose. And please, once you've consolidated that information in your mind and you're happy and you're ready to go on, join us again for the next module where we'll look at some of the in-memory capabilities in SQL Server 2014. Well, hi and welcome back to Module 5 of this course on implementing databases with Microsoft SQL Server. We've covered a lot of ground up to this point. It's been a fairly long day for both of us so far. we've covered tables, we've covered indexes, we've talked about stored procedures and functions, and we've talked about transactions and isolation levels and locking and all of that good stuff. We're going to switch gears a little bit in this module and talk about some of the in-memory capabilities that have arrived in SQL Server 2014. Now, for those of you who are preparing for the exam was originally based on SQL Server 2012, and so of course didn't cover any of the new technologies, but it has been updated and revised with some additional objectives and additional questions that cover the 2014 additions to the product. And most of those changes in 2014 relate to the in-memory capabilities. So if you are going to be sitting the exam, then you do need to have an awareness of these 2014 specific technologies. So that's why we're going to cover them. Christian, do you want to tell us what we're going to look at in this module then?
Sure, thanks Graham. So first of all, we're looking at the in-memory features that are predominantly new for SQL Server 2014, but I'll talk about the specifics of that shortly. So the first feature we're going to have a look at is the buffer pool extension, or BPE. Then we're going to talk about column store indexes, which were introduced in SQL Server 2012, but we've had some changes and enhancements in SQL Server 2014, so we'll talk about those differences there. And then finally, we'll finish off by talking about in-memory OLTP, which is a brand new kind of headline feature for SQL Server 2014.
All right, fantastic. So let's start with the buffer pool extension then. Tell us
Great.
about that.
So the buffer pool extension, so the idea behind the buffer pool extension is that it enables you to extend SQL Server's cache to non-volatile storage, and what we mean by that predominantly is very fast storage. So solid state storage is really this kind of target, and you can think of it like a Windows paging file, if you're familiar with how that works,
okay,
but for SQL Server. So what we're looking at is clean pages, so committed data that sat in SQL Server's data cache will be paged out to this buffer pool extension that isn't as fast as RAM, but is faster than the traditional spinning disks that you might use. So it's really easy to set up, and we'll see that in a demo, but a couple of interesting scenarios for this. So the first thing to mention actually is that it's a feature that's available in SQL Server Standard Edition. And the first scenario that I kind of think about for this is around virtual machine density. So if you think you have a really large host, a Hyper-V host with, let's say 256 gig of RAM, and you need to host some large SQL servers on that host. Let's say you want 4 64 gig SQL servers on there. So that's fine, and you can give each one 64 gig. But if you use this buffer pool extension, you can really extend the usage of that and maybe give, each one 32 gig, but a buffer pool extension of 128 gig, so that you can provide each one with a lot more kind of usable buffer pool space. So the idea is that you could get more on a physical box than you could if you didn't use this type of technology.
So you're substituting your actual RAM in the sense of memory chips in the server for fast storage, where if we went to a traditional kind of mechanical disk, there's a significant performance difference in reading and writing data between RAM and disk, whereas if we go to a solid state disk, then it's somewhere in the middle. It's nearer to the RAM level than the mechanical level, so it's going to be quicker
true.
to
and it's certainly true that RAM is relatively cheap these days, but when we're looking at consolidating and virtualization, everything has a cost, and the more we can sweat these assets, if you like, the more kind of options that we have around kind of configuration and getting the best out of things.
I guess it's worth pointing out, I probably should have said this up at the top of the slide. This module is about in-memory technologies. This isn't specifically an example of in-memory technology. If anything, it's almost the opposite of that. But what it is doing is kind of addressing the importance of how we manage memory and how we manage data that is perhaps temporary rather than volatile, rather than permanently persistent to disk. And in this case, we're talking about something that SQL Server does anyway. It does a pretty good job of managing the cache, so that data that's accessed frequently is held in RAM. What we're doing is just being smart about extending that out to free up RAM for other processes, or as you say, if we're consolidating multiple servers on the same physical box, but still getting the performance benefits of caching by using fast storage to take the place of the RAM.
Yeah, exactly. And another scenario that I've really kind of considered for this, and that we've used with a few customers actually, is around public cloud virtual machine density. So you can get Microsoft Azure virtual machines with SSD storage presented. Now, the bigger the virtual machine, the more RAM, the more expensive it is, as with any kind of public cloud provider. Now, you could get a relatively small virtual machine with, say, I don't know, 8 gig, 16 gig of RAM with standard edition SQL Server. Standard edition has a limit of 128 gig of RAM, but you could then extend that onto the SSD provided with the VM, and really get this massive buffer pool. So you could extend that by 128 gig, 256 gig. You know, the idea is that you'd have a VM with 64 gig, and then you have a buffer pool extension of 256 gig. So you're enabling the product to do more with those resources without having to get a virtual machine that's 5 times bigger and upgrade to Enterprise Edition as well. So it gives you a lot more kind of configuration options to be creative with the solution.
So frequently accessed data that traditionally you would cache in RAM in order to get to it quickly. If you don't want to, pay for that amount of RAM that you would have in a public cloud hosted server, you can move that to fast storage in effect, and get a lot of the same benefit from caching it, but without paying the cost of having to have that RAM.
It's not going to be as effective as having all of it in RAM.
Sure.
But standard edition of SQL Server is limited to 128 gig of RAM, and this is a way for you to provide 256 gig of RAM, albeit a level 1 and a level 2 style RAM. But that may suit the needs of your application, give you a bit more kind of flexibility around that.
Oh, very nice. So let's take a look at just how easy it is to set that up.
So it's really, really simple to configure. So all I'm going to do is alter server configuration. I'm going to set the buffer pool extension to on, and I'm going to specify the file that I want to use for my buffer pool extension. So in this case, I'm going to create a 10 gig file, and SQL Server is automatically going to use that as an overflow for RAM. So let's just enable that.
And in this example, you've done that in the temp folder on C. I mean, obviously, just for the demo that works. In reality, we'd do this to perhaps a dedicated, probably a dedicated SSD device for this.
So the ideal scenario for this is that you would have very, very fast solid-state storage, and maybe even storage that plugs directly into the motherboard, so you're not going through the disk subsystem. That's really where you're going to get the best performance out of this. But the idea is you would put it on the best storage that you have, or the fastest storage that you have available.
Okay, great.
But yeah, obviously I'm running on my laptop, so I've only got a C drive. So now that's enabled, and we can actually have a look in the buffer pool extension configuration to see the details. So we can see that it's enabled and it's been set to 10 gig in size.
Okay.
We can also have a look at DMOS buffer descriptors. Now, this DMV is going to return 1 row for every page that is held in cache, so this data cache.
Okay. Regardless of whether that's RAM cache or...
Exactly.
Okay.
So, and then what we see from here, so we've got 1 row for every page in cache, and we now have this new column in 2014 is in buffer pool extension.
Okay.
So we can see when we're writing queries to analyze the configuration of the server, we've got the amount of data pages here, which databases they're from, and file IDs. So we could write quite complicated queries to really kind of pull out how much cache a particular database has in RAM, how much of that is being moved to the buffer pool extension. But the whole aim behind this concept is that you would enable it, and SQL Server will just use it in the background if it thinks it would benefit from it. So you don't need to do any more configuration than that.
Okay, yeah, fantastic, sounds good.
Switching it off is as simple as buffer pull extension off. And there we go.
It's off.
Yeah. So it's very straightforward. It's easy to switch on, easy to switch off. If the drive that it's running on runs out of space or are there any problems there, it will automatically turn itself off. So it's a very easy configuration to set up and just maintain and run in the background.
Right, yeah, I was going to ask you what happens if the drive gets pulled and the system detects that that's happening.
Yeah, because the only pages that will be moved to the buffer pull extension are what we call clean pages. So these are committed pages that haven't changed, whereas a dirty page is something that would be in main RAM that maybe we've changed in RAM, but that hasn't made its way down to disk yet. So we're only going to move clean pages out to the buffer pull extension. So if we lost that disk, we've got no data loss at all. We just dropped stuff from cache.
We're not losing any transactions by doing that.
Exactly.
All we've done is lose the whatever was in cache, and the next time it gets queried, it'll be brought into cache.
Exactly.
Okay, great. Well, let's go back to the slides. All right, so that's the buffer pool extension. The other thing you mentioned right at the beginning was column store indexes, and I know these were around in 2012 and they've been enhanced in 2014. So tell us a little bit about those.
Yeah, so fundamentally, a column store index it's a different way of SQL Server storing the data in a table effectively. So what we have here on the left is a traditional row store. We've got two boxes there representing two different pages, and we've got 4 rows on each page there. Just get my screen together. And on the right hand side we have a column store index where it's been stored in a completely different way. So for the row store, on all of the columns for every row are stored within a single page. So if we take this example of data page 1000 on the left there, I've got 4 rows and all of the columns for those rows.
So a row can't span multiple data pages in that scenario, right?
Yeah. And then we've got another data page, and then we've got another 4 rows there. So, and that's the traditional way that SQL Server works and stores pages. But in this kind of data warehousing scenario, so we've got large scale reporting and large tables, so we've de-normalized the table construct, and we tend to have very wide tables. When we're doing reporting off those tables, we tend to report on really a subset of the columns in the table. So we're not returning all of the columns, we're returning a subset. And if we're returning a subset of columns, row store isn't the most efficient way of storing those rows. So this is where column store comes in. So the diagram we have on the right hand side, we've got 3 pages there, but each page only contains data for a single column.
Right.
So they're all 8K pages. So, and if you think how many, the number of rows that you can store on a page will depend on what columns you have and the data types, because that influences the size of a row.
Sure.
And it's all got to fit within 8K. But whereas on a column store, if you take a single column, you can store many more rows for that one column on a single page than you could if you had all of the columns. And this is the first principle behind this column store technology, because if we're reporting off a subset of columns, in this example, if I wanted to find all of the order dates, or I'm doing a calculation on the order dates or whatever, if I'm reading a single 8K page there, I can read 4 times as many values than I could as if I was reading order dates from a traditional thing. So I'd have to do 2 8K reads instead of 1 8K read. So this is the first area where we're making a lot of savings in reading lots of data at once.
So that's the first area. I guess the other thing here is compression. We know that
Exactly.
column store takes advantage of the same technologies that we use in things like Power Pivot, which is a technology for Excel, where we're able to store huge amounts of data in memory by using in-memory compression. So how does that play into this story?
So the compression, so as well as storing column level data, we're also going to compress the data as well. So that means we're saving in 2 areas there. We've got a a lot more of one single one single column on a single page, and it's compressed. So the amount of the volume of data we can read from a single 8K page is a lot more than we could read in a traditional row store model.
Sure.
So it's all about speed of reading, and the idea is that you can read so much that you could do aggregations on the data on the fly instead of having to do these pre-calculations.
Oh, nice. Okay. So let's look at some scenarios for where we might want to use this. Clearly, if this was a panacea, we would just change the way that SQL Server stores data all the time. So there are some scenarios where this is more appropriate than others. Let's talk about some of those.
So it's really most suitable for, although as a technology it will work, it's really designed for data warehouse scenarios. So we're looking at star or snowflake schemas. So for those of you that have work in the BI world or have done the data warehousing exams will be familiar with these terms. Tables that have a large number of rows. So if you don't have very many rows, you're not likely to gain from the fact that we've got an enormous density of rows per page.
Sure.
And data that responds well to compression. If you've got a table full of GUIDs, it's not going to compress very well.
No.
So we're looking at lots of repeatable data. Text data is really going to compress really well and is really an ideal candidate for a column store.
It's worth thinking about how compression works in many different ways, but it's worth thinking about the idea that in a data warehouse scenario like we're talking about here, where you've got a star or a snowflake schema, the fact that you've denormalized the data means there's duplication. And duplication is a great friend if you want to compress, because instead of storing the same value 100 times, you can store it once and say, yeah, the next 100 rows store the same value as this one. So you can compress very, very much that way. All right, well, let's look at different types of column store index. And then people who are familiar with SQL Server 2012 but not 2014 might wonder what we're talking about. So let's talk a little bit about that.
So a custom column store index is brand new for SQL Server 2014, and it's a much lauded feature. When column store indexes came out for 2012, they were fantastic, but one of the limitations was they were read-only. So the fact that we've got this clustered column store index in 2014, where we can create this index and read and write to it, is a real boost in the applicability of this technology to far more wide-ranging scenarios.
So yeah, absolutely. When you create we talked earlier on in one of the previous modules about clustered and non-clustered indexes, and
we did, yeah.
Roughly speaking, the same sort of rules apply here. You can have one clustered column store index. As it happens, if you have a column clustered store, a clustered column store index, it can be the only index on the table. You can't have any additional indexes. Because it must include all of the columns in the table. So effectively you turn that table into a table that's stored in this columnar format, and that cluster effectively defines the table.
Exactly.
So that's our clustered column store, and as you say, that's updatable. We've still got the non-clustered variant from the previous version. So.
Yeah, exactly. So non-clustered column store indexes was the feature that was enabled in SQL Server 2012, and we still have that as an option there, in the fact that we could define a column store index as a subset of columns in the table. We can combine it with other indexes as well, but one of the limitations, the big one, is the fact that it makes the table read-only. So the way that we would have got around that in SQL Server 2012 is that you'd have nightly table loads, and then you'd create the clustered index, non-clustered column store index, and then you would use that for read workloads during the day.
And there are very, I don't want to give the impression that, hey, you should throw away all your non-clustered ones and use clustered ones because those are updatable. In that data warehousing environment that we're talking about, actually your fact tables tend not to be updated very often anyway. They tend to be read-mostly databases, I guess. And even when you are updating them, if you've got a non-clustered index, particularly if it's, let's say, a partitioned table, which is not uncommon in a data warehouse, you can create the non-clustered column store index on the table. You can create a table with a matching non-clustered index, and you can switch the partitions. So you could actually, load the new data that you want to add to your fact table, create a non-clustered column store index on that, which will be fairly quick because it's only the new rows that you're adding on a daily load, let's say, and then switch that partition into an empty partition in the fact table, and you're able to update the table in that technique as well. So there's, it's not it's the end of the world, it makes the table read-only. There are techniques you can use to make effective use of these things. But certainly the clustered column store index, where the table is updatable, on a day-to-day basis, makes it easier to do those kind of ad hoc inserts and updates and so forth. Yeah,
absolutely. Should we have a look?
Yeah, let's take a look.
Okay, so I'm going to use the AdventureWorks Data Warehouse database for this one. I'm going to execute this query, a couple of joins, just to get it into cache. Now I'm going to set statistics time on and statistics IO on, because we want to compare and contrast the execution times for this. And I'm going to run this query. Take a measure on the messages here. So what we're looking for here is this. So we've got a CPU time of 1766 and an elapsed time of 909 milliseconds.
Okay.
So let's take these stats off. We're going to create a non-clustered column store index. A second to create. So we try and insert a row here, which will fail. Why will it fail?
It'll fail because it's a non-clustered column store index, so the table's read-only.
So it's read-only. So we can't update a table with a non-clustered column store index. But we can read from it. So let's set these statistics back on and see if we can spot an improvement here. So we've now gone down to 483 of CPU time. So that was 1766. So what's that? A third?
Yeah, that's a significant improvement.
Before.
And if you think, the larger that table would be, the more dramatic the improvement
Absolutely.
would be. It was pretty quick to begin with because it's just sample data, but if you had a query that took several minutes to run, cutting that by a third is actually a fairly significant gain.
Yeah, or 2/3 in fact.
Yeah, indeed, yeah.
So let's switch those timings off again, and let's drop that index. And we'll create a clustered column store index, so that's going to affect all of the columns. Notice now that we can insert the rows that failed
So the
previously.
table's updatable like a regular table.
We'll switch that on. Hopefully. So, and again,
it's there or thereabouts. It's just a little slower in this instance, but other factors would affect that. It should be comparable to the non-cluster.
But from the original query, it's still more than 2/3 faster, which is quite significant. It's quite a significant gain.
I guess just before we switch away from the demo, one thing I do want to sort of add to all of this, we've talked about the fact that a clustered index is updatable and a non-clustered, other than using various techniques, makes the table non-updatable. I just want to kind of explain a little bit of how that works under the covers, because when you use a non-clustered column store index, one technique that's quite often used is you have your table, which contains your data, but you may create something that goes along with that table, another table that has the same structure, which you use as a kind of temporary writable space. And when you query your table that contains the non-clustered column store index, you union the results with this, let's call it a delta table, which contains the changes, and then periodically you merge those in. So there's a technique where you can implement some logic to effectively combine two tables into one logical view of the data and then periodically merge the changes in. And actually, under the covers, that's how a clustered column store index works. Internally, SQL Server maintains a traditional row-based delta table portion of that table plus the column store in memory part. So when you do an insert or an update, what actually happens is that delta store table is modified, it's stored on disk until we reach a threshold where a certain number of pages have been updated, and at that point under the covers, SQL Server will take those and absorb them into the column store area. So there's a certain amount of additional complexity under the covers when you use these things that you might not immediately be aware of. And there are dynamic management views you can use to see, well, what's currently in the Delta store versus what's been absorbed into the table itself. But it's worth being aware of that.
Yeah, excellent.
Okay, let's switch back to the slides. And moving on from there, let's look at, I guess, what most people will think of as the in-memory feature for 2014. This was the big headline additional new capability in SQL Server. The code name was Hackathon. For a while we had lots of people talking about Hackathon. So if you do hear that word, it refers to this technology that we're going to talk about now. So Christian,
Perfect.
take it away.
Thanks, Graham. So in-memory OLTP, as Graham said, is the brand new feature for SQL Server 2014. The code name for it was Hackathon, and it's still kind of referred to as Hackathon. It's a bit easier to say than in-memory OLTP. But certainly for the purposes of the product feature in the exam, it will be in-memory OLTP. So it's essentially a high-performance OLTP feature. So online transaction processing is the target scenario for this. And it consists of two parts: memory optimized tables and natively compiled store procedures, which are used to access memory optimized tables.
Okay, so let's deal with the first of those two things, and let's look at memory optimized tables.
So let's have a talk about what are memory optimized tables. So what's quite interesting in the fact that this in-memory feature for SQL Server was really designed with two parts in mind. It had to be part of the product itself, not an add-on product, and it needed to be integrated. So you didn't have to have an in-memory database. You could take the parts that were relevant to you and put them up in memory. And the first thing is a memory optimized table. So when you make a table memory optimized, SQL Server will actually take that definition as a C structure and compile it into DLLs and load it into memory. So every time you then insert into that table, what's happening under the covers is that SQL Server will be using DLLs to interface with that table, because it's not a normal table structure anymore.
So it's actually it's converting your transact SQL that you use to create the table is converted to C, which is then compiled to a DLL, and that DLL is loaded. That's what's in memory, that DLL.
Exactly. So it's very, very high performance and very efficient. So we don't have any locking semantics on the in-memory tables. So we don't have any locking and blocking problems. So everything will run using snapshot-based isolation levels. We can index using hash indexes. Okay. It can coexist with disk-based tables, and this is really the key thing for integrating this technology into existing applications. As I mentioned before, you don't need to have this separate database, this separate application that you're rewriting. It can coexist with disk-based tables, and you can also query a memory optimized table using T-SQL as well.
All right, so I don't have to write any different code. I get query it just like an ordinary table using a transact SQL.
Yeah,
system.
exactly.
Oh, okay,
exactly.
great.
So scenarios for memory optimized tables. So the real key scenario where you get the most benefit from this is where really kind of high concurrency scenarios where you've reached the scalability limitations for the traditional architecture around SQL Server. And this is this limitation around locking and latching. So regardless of how fast your memory is or your disk is, we're still bound by this fundamental structure of latching pages in memory and the blocking that's associated with those. So without those latching mechanisms, the throughput that you can get and the scalability is much greater when you're looking at memory optimized tables. Right,
and we talk about hot pages there. I always, whenever people ask me about this, I always sort of explain this as being, imagine you've got a table of orders and you have an incrementing order ID key, and you've created a clustered index on that key. Well, what that means is all the inserts are going to happen in the last page.
Exactly.
So if you've got lots and lots of client applications trying to insert data at the same time, they're all going to be on the last page. At some point that page is, we're going to escalate a lock to page level and start blocking any new orders being taken. So those types of structures, which make sense in themselves, can lead to you having pages that are particularly commonly accessed, and those become your hot pages. and that kind of leads to a lot of blocking.
Yeah.
So this type of technology is really designed to deal with, you've got an application design that gives you this hot page, that leads you to an awful lot of locking and blocking because you've got lots of concurrency. How do you deal with that?
Yeah, and it's really targeted at massive scale.
Yeah.
You know, the scenarios that this fixes, it's not that the product doesn't work, it's the fact that you're trying to do so much against these tables that you get these hot pages, and SQL Server will manage concurrency on those pages with latching, which is a lightweight locking mechanism. And because we don't have any of this, these locking semantics, and we don't have latching involved, the throughput that you can get from that is much, much higher.
Okay, great. So let's look at how we actually create these things then. I see we've got a number 1 in the slide title, so I'm guessing there's multiple steps. So why don't you talk us through?
Yeah, sure. So the first thing we need to do is to add a file group for memory optimized data. So we've got an alter database here. We're adding a file group that contains memory optimized data. So this is a very specific file group that's going to take file stream data. And in the next statement here, we're going to add a file, specify the file that we're going to add, and it's added to the file group memdata in this example.
And I guess in case you're confused, we're talking about in-memory data, and you might be wondering, well, why do we need a file group? It's just purely a semantic of the way that tables are created in SQL Server. Yeah. Tables are associated with file groups, so we have a file group that's effectively there as a placeholder for, you know, really the metadata that defines that table. And when we persist, you know, although it's held in memory when we're using it, it's persisted to disk so that it survives restarts of the server. So that's why there's a file group associated with it.
So the next slide then is around creating a memory optimized table itself. So we're using the normal create table statement here, but we're also adding a couple of extra commands in here. So we're adding a non-clustered hash index here with a bucket count. Mm-hmm. So this bucket count is the number of hash buckets that we're going to make available for this. And the number of buckets that you should have ideally should be the number of unique values that you'll have in that column. Mm-hmm. But it's flexible enough that you can have non-unique values, and it will link those together.
It's perhaps worth just stepping back for a minute before we finish talking about the overall syntax. One of the things that's different about memory optimized tables is the indexing, because indexes, as we know from previous modules in traditional tables, are disk-based themselves. They're pages that are stored on disk, and they may be cached, but fundamentally the index is stored on disk. There are two types of index that we can use with a memory optimized table, and this variant that we've got here is a hash index. What actually happens is that the key or keys that you're the key column or the key columns that you're using for the index, a hash algorithm is applied to them to generate some sort of unique value that you can get from those values. That then determines which location in memory this row is going to be stored. So it's very much a case of we hash the value that's the index key. That identifies effectively a pigeonhole in memory in RAM where we're going to put this row. Now, of course, it's possible that two values will hash to the same value, so they'll end up in the same location in memory. And if that happens, what's then stored in memory is the first value that was put there with a pointer to the second one and a pointer to the third one. So you end up with what's called a linked list structure. And this type of index, a hash index, is very, very efficient if your queries are searching on equality predicates. So if I want to find all of the sales where the customer name is Malcolm, I would search for equals Malcolm. It's an equality predicate. So it hashes that one value, Malcolm, goes and finds the location memory where the Malcolm records are stored, and it finds them very quickly. There is an alternative type of index called a range index, which conceptually is very similar to the more traditional SQL Server indexes we know of that are kind of binary tree type structures. Again, it's in memory, so it's not exactly the same as a traditional sort of clustered or non-clustered index we'd create for a disk-based table, but those are more effective if your queries are likely to search for ranges of values. So find me all the transactions between, November and the following January. That's a range of values you're trying to find, and that's going to be more efficient than trying to calculate all the individual hashes that are possible between those values and find the locations in memory. So we're kind of just showing you the syntax. Hash we've highlighted because it's new. It's you won't have seen that type of index before. It's not the only game in town when it comes to indexing in memory tables. So you need to consider that. Anyway, I've probably diverted us far enough.
No, that's fine. That's fine. If we move the slide on, actually, there's a couple of points there, just reiterating what
there you go. I peeked too soon.
What Graham was mentioning. That's fine.
So let's move on to talk about querying memory optimized tables and try and understand a little bit about that.
Yeah. So first of all, we mentioned at the beginning that you can have a memory optimized table, and that you could write a query that accesses a disk-based table and a memory optimized table as well. And the way that it enables us to do that is through this query interop. So we can combine the two together.
Okay.
And the other way that we can access tables is through native compilation. So this is store procedure converted to C and compiled, where you can access only memory optimized tables. So what's interesting about the native compilation is that when you write a store procedure normally, T-SQL is an interpreted language. So while we have it compiled, it's essentially interpreted. So when we execute the code, it has to line by line execute what you're trying to do, which is fine under a traditional model, because we're so dependent on disk-based tables that having an interpreted language to access those tables was an insignificant cost in the wider cost of execution. But now we've got these structures that are memory-based, and they're not just pinned in memory. They're actually memory optimized structures that we can get significant savings, not just by having a table that's optimized to be in memory, but for optimizing these store procedures as well. And when you natively compile a store procedure, it's compiling it into C code and presenting this compiled C code that is far more efficient to execute.
So the path that we've got there, though, if I've got a natively compiled store procedure, it can only query memory optimized tables. I can't use that to query.
That's correct.
Right. Okay.
Yeah. So we can have a normal query can read from both, but a memory optimized store procedure can only access in memory tables.
All right. Perfect.
Should we have a quick look?
Let's have a look.
So let's have a look at memory optimized tables first. What we're going to do here is to create a new database specifically for this. So let's do, let's just keep it simple and do create database memdemo. So now we're going to go into the properties of this new database.
So far it's just a regular database. There's nothing special about it.
Absolutely. I'm going to create a new file group in the memory optimized section down here, you'll notice. And we're going to call that MFG. And now we're going to have a look at creating a new data file. We'll call that let's call it memdemo2. And we're going to put that, we're going to put it in. So this new file type we have here is file stream data. And because the file group that we've created is memory optimized, it's the only file group that's available for file stream data.
You should point out that there is a technology called file stream that's about storing files in SQL Server, or at least storing documents in SQL Server, and they're spilled out to the file system. This is potentially confusing here. We're using the same type of file group as you would use for file stream storage. We're not using file stream storage in the sense of that feature. We're just using that same type of file group to store memory optimized data.
Exactly, yeah. So let's create that now. So now what we're going to do is to use this database. We're going to create a table that's optimized for in-memory. We've got this non-clustered hash with the bucket count, so this is exactly what we saw in the slide.
Mm-hmm. And just again to interject, I detracted earlier on when we moved. I diverted us off when we talked about the syntax. So we didn't really have a chance to talk about this durability flag that's here, this option. And again, it's probably worth mentioning there's two different options. This one here is schema and data. So what we're saying is any data that's inserted into this table or updated will be persisted to disk. So that if the server goes down and comes back up, we don't lose the table.
Yeah.
Why would I ever want to have durability just the schema and not the data?
So you can think of a scenario where you don't need to persist the data. So you're looking to have data temporarily that's held in memory, and you may want to have durability on the schema and not the data as well.
So maybe session data, I guess, for a website or a shopping cart that. If the server goes down, okay, we lost the shopping cart, but it wasn't a persisted order or whatever.
Exactly.
Oh, okay.
Exactly. So we've created that now, and what we're going to create for comparison is the same table as a normal disk-based table.
So this is the same structure, but it's a traditional
exactly the
table.
same, exactly the same structure. Yeah. And then we're just going to insert 500,000 rows into the disk-based table, and just have a look at the timings of that.
And you're doing that within a transaction, so it's going to lock as we do that.
Yeah, exactly. Yeah. So that took 6 seconds to run. I don't know if you can see in the bottom right-hand side of my screen. Mm-hmm. And if we just have a look at the contents of that table, we've got 500,000 rows there.
Okay.
So and now we're going to do exactly the same thing into the memory table. And that's taken 5 seconds to run. So I was expecting it to be a bit quicker than that, but it's still better than it was onto the traditional table.
Okay.
So let's have a look. So we've still got 500,000 rows there. Right. Now let's have a look at a delete. So if we delete from the disk-based table, so that's taken a second to do that. And if we delete from the memory table, so we're sub-second on that. So the scale that we're running on this, it's always quite difficult to work out the scale because the laptops get faster and faster and faster. Sure. So the performance gains from a demo perspective can be quite small, but hopefully what we've demonstrated here is the interaction we've had and a comparison between a disk-based table and a memory-optimized table. Right. And there are performance gains that we had through that process.
And I have seen demos where it's a much more dramatic difference as you scale Absolutely. Up. As you see, your laptop's clearly a very powerful laptop, so the disk-based table is performing well. Yeah. But I've seen demos where the disk-based subsystem is significantly slower, and the semantics of the locking is significantly slowing things down. So there's a dramatic difference between the time it takes to run those two.
There are a few times with this laptop where I regret the fact that it's got very, very fast SSD storage when I'm demoing the difference between it and the memory.
So what you're saying is if I'm implementing an enterprise system, I should either use in-memory technologies or I should use your laptop.
My laptop.
That's the time. Okay.
And then finally, we've got some memory optimized stable statistics that we can get pulling this out of this additional DMV that we have for in-memory.
Oh, so I can actually keep track of, because obviously the data is in memory, I want to keep track of, well, what's that doing to my overall memory usage?
Yeah, exactly. So it is quite useful.
Okay. Can I ask you, just before we move on to the next little section, could you bring up the file explorer and let us have a look at the file system? Because I think it's probably worth exploring a little bit about what's being created. So if we're going to where our SQL Server databases are stored.
It's probably...
If it's 64-bit, it'll be in there.
Yeah.
Yep, so
take a guess.
No, it's not that.
The other one.
So into the data folder, there's an XTP folder. Let's have a look in there, and into 9. And you see a bunch of files here that have been generated. Now, these have been generated by SQL Server, and anybody who's done any software development will recognize some of these that are object files and PDB files and out files, which are used as part of the compilation process to ultimately produce that DLL file, which is the DLL representing our table. And I guess what's really interesting is right at the top of that list, there's a C file. So if you can go ahead and double click that guy, and let's open that up in Notepad. Here's the actual C source code that SQL Server has generated to represent that table. So there's a struct in here that is used to implement that table, which will have all the public fields that are the columns in the table. So you can actually drill right under the covers and see what's going on when SQL Server actually generates these in-memory tables.
That's really good.
And we talked about our tables. One of the things we didn't see in the demo there that we mentioned earlier on was natively compiled stored procedures. So let's have a little chat about those.
So we've mentioned this before when we were talking about this query interop where you could write normal T-SQL and you could read from a disk-based table and a memory optimized table. And we've also talked about this idea of natively compiled store procedures. And again, just to reiterate this point, is a traditional store procedure. T-SQL is an interpreted language, which was never a problem when we're working with disk-based tables. But if we're working with things in RAM, which is really, really fast I/O, we can get a lot of performance gains if we can compile these store procedures into a C structs like we've seen with the tables as well.
Okay, so I can see some differences in the syntax there compared to creating a regular stored procedure. The obvious one is the with native compilation.
Yeah.
We've got schema binding, which we saw before when we talked about views. The idea is if anything underneath this, anything this thing depends on changes, well, actually don't allow anything that this thing depends on to change. We've got the execution context, so who is this going to run as? And in this case, it's going to run as whoever the owner of the stored procedure is. And then I've got something that looks like a transaction, but the syntax is different from what we've seen. It's begin atomic with, and then I specify an isolation level for this, and it so happens you also have to specify a language, which is part of the requirement. So I guess it's worth being aware of that. The reason this is different from the semantics you've seen when creating transactions in Transact SQL for ordinary stored procedures is again due to the fact that it's stored in memory. So the underlying semantics as to how this is done is different, and this syntax is baked into the DLL that gets compiled. But the effects are the same. Effectively, we'll end up with this being a transaction that uses snapshot level, isolation level. Yeah. Okay, so we'll hop back to the demo machine.
Should we round up with a demo of these compiled store procedures? Okay, so we're going to use this same database again, just to make sure we're in there. So this time, instead of running this code to insert these 500,000 rows, we're going to create a natively compiled store procedure called insert data. And we're going to execute that store procedure. So can you remember how long it took to insert
into the memory optimized table when we just ran the Transact SQL? It took 5 seconds.
It was 5 seconds and 6 seconds for the disk-based table. So let's see how quickly this is. So less than a second.
Wow, it's instantaneous. Yeah.
So there's a massive difference. So while we had a performance gain of switching from disk-based table to memory optimized, the real massive gain we've got there is by switching to a natively compiled store procedures to do the same operation.
Fantastic, brilliant. Okay. So we covered a number of things in that module. We talked about the buffer pool extension, which was not an in-memory technology per se, but a way of taking data that's normally cached in RAM memory and moving that out, spooling that out onto a fast disk, a fast storage device, so that we're making more use of our fast solid-state storage, and we're able to maximize the way that we're using our RAM and get better use from fast storage. We talked about column store indexes, both the non-clustered variety, which have been around since SQL Server 2012, all those years ago, 2012, and also the clustered column store indexes in 2014, which, if you remember, are updatable, whereas the non-clustered
Yeah,
ones make
that's
the
correct.
table non-updatable. And then finally, we talked about in-memory OLTP, or Hekaton as the code name was, where we talked about memory optimized tables and those memory optimized stored procedures that we've just seen, where you can see some significant performance benefits in particular workload types.
Absolutely.
So, I hope you've enjoyed this module. Again, the usual rules apply. Go off and have a look in SQL Server books online, research this stuff, play around with it for yourself, make sure you're comfortable with that technology and with these different techniques. And then come back and join us for the final module in this course, where we'll look at optimizing and troubleshooting performance. So I look forward to you joining us then. Well, we made it. We're at module 6. We've made it through to the final module of the course. Hope you're all still with us out there. We're going to finish off the course with a look at optimizing and troubleshooting queries. We've talked a lot about different techniques for implementing a database throughout the course. And at the end of the day, databases are about accessing data. And for a lot of users using applications, the area they're going to get concerned about is the performance when they're doing that, and when things go wrong, how do we make sure we optimize that performance? So, Christian, I'm going to ask you to tell us what we're going to cover in terms of optimizing and troubleshooting.
Great, thanks, Graham. So for this module, what I wanted to really talk about is a few things really around kind of optimizing and troubleshooting tips. So the first thing that I wanted to talk about is SQL Server weights and the concepts and architecture that supports the idea of a weight, and then we'll talk through a specific scenario that from within my role we see a lot of these kinds of problems around joining too many tables, and I'll show you why that's a bad idea in terms of how the optimizer works, and then finally we'll have a slide at the end where we can have a discussion around some other performance tuning tips that have maybe been sprinkled around these 6 modules, that we can consolidate those and close off the course.
Good enough. Okay, let's start with weights.
Great. So if we think about the way SQL Server works, first of all, and we'll walk through this diagram. So when you connect to SQL Server, you'll connect in the context of a session. And then which we would track with a session ID or a SPID in old money if you've been around SQL Server for a while. And then when you execute something, so you execute a piece of code, SQL Server will generate a task, which is this kind of internal structure that's used to provide a context for the execution of what you're trying to use. So we have this task concept. Now this a task will then be assigned a worker thread. So a worker thread we don't actually have on this diagram. So we have a session, a task, and we'll have a worker thread that is assigned to execute the tasks. So when we talk about things running, the only thing that actually runs is a thread, is a worker thread. It's just we kind of abstract it all the way up to an application or a user or whatever. Okay. So we have this session, task, and worker thread. So the worker thread will be assigned to what we call a scheduler. Okay. And the scheduler's job is to schedule time for workers to execute on a processor. So by that I mean a logical CPU, as we have in this diagram. So you may have hyper-threading, you may have virtual CPUs. SQL Server doesn't care about what your kind of process architecture is underneath. When SQL Server starts, it will look at the number of CPUs that it sees when it starts, and it will generate one scheduler per CPU.
Okay.
Okay, so and we call this scheduler, scheduling time for threads on a CPU, we call this a cooperative scheduling model. So this is SQL Server's scheduling model of scheduling threads on CPUs.
So I guess when we're talking about multitasking is the term people use when they talk about how computers do their work. Of course, what's happening is you've got a query that might take a long time to run, and you've got other things that are running as well, and we're effectively time slicing, where we're sharing that CPU across lots of things that are happening.
Exactly.
And the thread goes on and off and on and off as it...
Exactly. So this is where fundamentally a CPU can only ever do one thing at any one time, and it gives the illusion of multitasking because it's switching between these threads very, very fast. We call that switching context switches.
Okay.
So if you ever looked in Perfmon and you have a look at context switches a second, so this is what it's referring to, flicking between worker threads on a CPU. Right. So if you see a high number of context switches a second, it's an indication that there's a large number of workloads trying to compete for time on the CPU.
For limited CPU resources.
Yeah,
okay.
Exactly. So, so we call SQL Server's scheduling mechanism a cooperative scheduler because while this thread, the thread that's running your piece of code, is running on the CPU, if it doesn't need CPU time anymore in terms of, in order for me to continue processing, I need to get some data off disk. It will voluntarily yield its time on the processor to let somebody else have a go. So it cooperates with other threads in order to provide a more efficient execution model.
Okay, makes sense.
Okay. If we just go back to that slide and we'll talk about the, as opposed to Windows, which has a preemptive scheduling model. So Windows is a general purpose operating system from my desktop to a powerful server. It's written specifically for multiple programming languages, multiple applications, multiple uses, and there's nothing to optimize Windows on my laptop over Windows Server specifically for any particular application. So this is what we call a preemptive scheduler. And a preemptive scheduler model, you get a time slice in order to do your execution. And whether it's convenient or efficient for you to stop, you'll get kicked off to let somebody else
Windows
have a go.
turfs you off to let somebody else use the processor.
Exactly. So, and this is where in the SQL Server 6.5 time frame, the SQL Server team created this cooperative scheduling model in order to control the Windows scheduler in a more cooperative manner.
Okay.
And this is all leading on to something important, I do promise. It's not just an exercise in how things work.
Okay.
So this leads us towards this SQL Server weights architecture. So when we talk about threads, so threads can be, for the purposes of this kind of understanding weights, we talk about threads being in one of three states. So the first is a running state. So this example, we have a thread running under the context of session ID 55 on scheduler 1. So on scheduler 1, we're assigned to a processor. Okay. And we can only have one thing running on a processor at once. Therefore, we can only have one thread on scheduler 1 in a status of running, and that's the thread that is executing on the processor.
Okay.
Make sense?
Yeah, absolutely, yeah.
So if you're not running, then chances are you're suspended.
Okay.
So, and when you're suspended, so this is an example of where, because we're running in a cooperative scheduler, I still need to run, but I need to get some data first. So rather than me holding up the CPU, I'm going to voluntarily yield. I'm going to switch my state to suspended, and I'm going to store information about what I'm waiting for. So anything that's in this suspended state is what we call a SQL Server wait.
Right, okay, that makes sense.
Yep. And the third state that I wanted to talk about is this runnable state. So we're running in this cycle of I'm running, I voluntarily yield while I wait for something from disk, for example. And then I get that information back, and I need to get back onto the CPU. So then I'll join the runnable queue. So I'm queuing up to get back onto the running state again.
Okay, so I've been on the merry-go-round, I got off to give somebody else a go, and now I rejoin the queue to get back on.
Exactly. So time spent, anything in the suspended state is what we call a SQL Server wait, and anything that is runnable is what we call a signal wait. So a signal weight is a way to track CPU pressure effectively, because anything that's runnable is effectively just waiting to get onto the CPU. So if we could have a look at signal weights, it would be an indication of CPU pressure.
Okay.
But the main area that I wanted to get across with this is this concept of a SQL Server wait. So we have 4 sessions in there that are running tasks. We've got a couple of wait types in there, which we'll talk about on the next slide, actually, in terms of useful wait types.
Okay.
So when we're voluntarily yielding, there will be places in the code that will log effectively what that thread is waiting for. And if we can track what threads are waiting for and aggregate those, we can essentially have a look at what the bottlenecks are in the system.
Right, okay.
So some of these useful wait types, so page IO latch, for example, is a latch on a page in memory. So if you wanted to read data from a table, everything that you do within SQL Server has to go into memory. So you do a select star from table name. That data has to go in memory before it gets sent out to you. Mm-hmm. So what SQL Server will do is to put a latch on a page in memory in order to, so it's basically saying, I'm going to use this in a minute, so nobody else use it, while I go and get the data to put into it. Okay?
Okay.
So this wait is, I've taken a page IO latch and I'm waiting for it to be filled. So a page IO latch is a pure wait on reading data from disk to put into memory. So it's an indication of slow IO if you've got a page IO latch wait.
Okay.
So the second one we have on there is a CX packet. So this is a synchronization packet. So this indicates that we have parallelism running on the system. Okay. It doesn't necessarily indicate a problem, but it's the synchronization between parallel threads. So you'll always get CX packet waits where you have parallelism.
And by parallelism, we mean there's multiple processors or multiple virtual processors.
Yeah, so we've got multiple processors. As we had in the diagram, we had 4 processors. Yeah. And if SQL Server determines that what you're trying to do is expensive enough to overcome the overhead of breaking it into parts and running it across multiple processors, it will run that query in parallel, and that's what we mean by parallelism.
Okay.
So a CX packet, rather than indicating a problem, indicates that we have expensive queries.
And we're trying to synchronize them across multiple processors.
No, it's actually, so if we have 4, we're running in parallel across 4 processors.
Yeah.
So that's 4 threads.
Right.
So we have each one of these threads will have a packet of work to do. So I'll give you each 2,500 rows to process.
Right.
So this guy finishes his first. So then he's waiting on CX packets because he's waiting for the other guys to finish. So what you end up with is several threads that are finished, and you've got one that ends up having to do more work than the others, and that's what you're waiting for.
I see. Okay.
Anyway, the short story for CX packet wait is that it indicates parallelism, which indicates expensive queries, and if you're running on an OLTP system, you're not really expecting big expensive queries to be there. So it's an indication that you would go and investigate and find these big expensive queries and see if they're expensive because they haven't been written properly, or that they need to be expensive in order to achieve the business logic.
Okay.
So the next one on there is write log. So write log wait is a wait to write to the transaction log. So this is a kind of a high level indicator of transaction log write performance. So there's a good indicator there. So LCK, do you remember we saw this earlier on?
We looked at locking, yes.
We did. We looked at locking. So one of the nice things about tracking and looking at wait types is that it's not just around resource utilization and resource waits, but it also involves locking as well. So what we saw during the demo earlier was an LCK on a shared lock. So we were waiting to get an exclusive lock that was being blocked by a shared. Mm-hmm. And we also have these preemptive wait types as well, which were new with 2008 actually. Mm-hmm. And preemptive, you remember where I mentioned preemptive earlier in this session?
So Windows preemptive.
So Windows has a preemptive scheduler. So whenever you see a wait type that is prefixed with preemptive, it means that SQL Server is waiting for Windows to return something.
Okay.
So a good example of where we've had that, we had a customer that had problems. Nobody could log into SQL Server, and or the application couldn't log into SQL Server, and we found that we could log in using a SQL Server account, but not with domain accounts. And what we found is when we had a look at the wait types, everybody was waiting on preemptive authentication ops wait type. And basically this was an indication that SQL Server was waiting to enumerate Windows groups from a domain controller, and we found that the domain controller was broken.
Right.
So by looking at SQL Server, we could tell the customer that they had a problem with their domain controller, because we had this new kind of preemptive wait types. And another one as well for anything that happens in the file system will also have a preemptive wait type as well. So if you're doing, a SQL Server needs to do an auto grow event, or you're creating a big file or anything like that, we'll also have a preemptive wait type for file operations. So you can see SQL Server, your query is not running, but you have a look at the wait types and you find it's actually trying to auto-grow a file on disk.
And we're waiting for Windows to finish doing that.
So it's really, I'm quite passionate about using wait types as a troubleshooting tool, because everything from a slow file system to a broken domain controller to locking problems, you can see within this kind of single view, which is really quite powerful.
Okay. So if I want to view these waits, up till now we've seen lots of different dynamic management views for viewing different things, and we actually saw one of these to look at weights in one of the previous demos. So
we did, yeah.
Let's start with those.
So the first one is really sys.dm exec requests, and you can think of this as I like to think of it as a replacement for SP_who that we would have used in previous versions, a store procedure to return who's doing what. So dm exec requests provides wait information at the session level. So remember we talked about sessions and tasks. You execute something and it spawns a task to run within this context.
Okay.
So if you think about an example of a parallel query, will spawn multiple tasks, but if you're having a look at dm exec requests, this works at the session level only. So you're not going to see the wait types for any more than one task that's sitting at that level.
Okay.
Does that make sense?
It does.
So it does provide a bit of information there, but what we're really interested in is working at this task level, and this is where we would use DMOS waiting tasks to find out exactly who's currently waiting for something.
Okay.
So I've said that this is it's very accurate in here because it's a live view on who's waiting for what at the time that you select from this DMV. And because of the nature of SQL Server and the way things execute, somebody is always waiting for something.
Sure.
So every time you view this query, you get this massive result set that flexes like this. So it's really useful for a live problem.
Right.
You get a call, everything's running slowly, what's happening? I would go and have a look in this DMV to see somebody's probably waiting for something, and it would have it on there.
Okay.
But if you've got lots and lots of users that are waiting for a very short time period, so it's not really noticeable, but over time that would have a cumulative effect on the overall performance. We would look at this final one here, which is DMOS wait stats. So wait stats stores, instead of a row for anything that's waiting for something, it's a row for every possible wait type, and then it has aggregated statistics of how many tasks have ever waited for that wait type, what is the longest time that anyone's waited for that wait type, things like that.
So it's historical data that lets me see, hey, I seem to have an awful lot of preemptive waits, for example.
Yeah,
maybe there's something in the Windows subsystem I need to look at.
And this is one of the first things that I would have a look at. If I was having a look at, I sat down in front of a SQL Server that's got performance problems, I'm really quite interested in what historically, since the last restart, have things waited for. And quite often you'll see obvious things will bubble up to the top, like preemptive or disk problems or locking problems, and you can get a good indication of why things are running slowly in the environment.
Okay, great. So I'm guessing
Should we
you're
have a
going to
quick
show
look?
us some of that.
Yeah, let's have a quick look. So what I wanted to do here is we'll switch back to this people database that we used towards the beginning of the day. We'll have a look at these DMVs first. So we'll do DM exec requests. So this is one row for any executing tasks, effectively. So there's lots of background threads. I'm going to modify these to do where session ID is greater than 50. So this is going to show me all of the user-generated sessions. So just to caveat that, anything greater than 50 will be a user. A user session will always be greater than 50, but there are circumstances in which system-generated sessions there's more than 50, so it will spill over.
Okay.
Does that make sense? So if I'm just looking for user sessions in general, I would use this kind of filter. So I've got two sessions here. I've got session ID 52, which is where I am. Let's just run that select statement. Let me take a copy of that so we can use it. If I have a look at DMOS waiting tasks, do you remember I mentioned this kind of transient view? So there are lots of things.
So this is what's currently going
waiting
on.
for stuff, yeah. But a lot of these things are benign waits. They're system threads waiting for something to happen. So anything that has sleep or poll or wake up, we would tend to ignore.
It's in the background.
It's waiting for something to happen. It's not causing a problem.
Okay.
But again, I would kind of filter that on session ID equals 50. So I've got 53 is waiting on a trace write, which is probably the trace that we were running earlier in the day is still running in the background. Yeah.
Okay.
So if we have a look at finally this DMOS wait stats. So this is one row for every possible wait type in SQL Server. Okay. So we've got information around the number of tasks that have ever waited, the total wait time in milliseconds, the maximum wait time for a single thread, and the signal wait time. Remember we talked about signal waits.
So we need to get back on the CPU.
Yeah, exactly. So what if I could ever... And if I was to give you one single query to run here, it's this sort of view of wait stats, of ordering this information by wait time in milliseconds descending. So what this is going to give me is a view of the total wait time in milliseconds that all the tasks running on my SQL Server have been waiting for things. And then I'm going to go down and I'm going to trim out wait types that are benign, basically. So we've got sleep task. So I'm not interested in any of these until I get down to CX packets. So we've got exclusive locks there. So this is from earlier in the demos. So we had a total of 125 seconds. And that was actually from a single thread waiting for an exclusive lock. So while on a busy server, that may not look like very much, but that was a single user connection waiting for 2 minutes for an exclusive lock. So I kind of flagged that. That's a yellow flag. I want to try and find out a bit more information about this. We've got some CX packet rates. When we were doing demos earlier on, we had some parallelism. We've got some update locks there. We've got write log. So I mentioned writing to the transaction log has been a bit slow. So you can see just from the demos that we've done throughout the day, because I haven't restarted SQL Server, I've got this background aggregated view of wait types that's enabling me to, if I had performance problems or I was unhappy with the performance of this server, I could really drill into this and find out what's going on.
So it's great for giving you that starting point for investigating, here's what we've been waiting on, let's figure out why we've been waiting on that.
Exactly.
Okay. Great. All right, well, let's switch back to the slides. So, I mean, I guess all of this really is about diagnosing performance, and the symptom that you're initially going to get from performance is typically that queries seem to be really slow in running. So, let's talk a little bit about that.
So here's an example on the screen of a query that ran slowly. So this is a kind of a real scenario that we had of a problem, and you can see that there are a number of joins in there. So it's not surprising that it ran slowly, but what's quite interesting about this is that it's not consistent in the way that it runs. And the reason for that is because of the amount of joins in there and how the optimizer works.
Okay.
So if we have a look at the next slide, we can see that when executing this this piece of code, so we talked about the optimizer and the SQL Server optimizer will look at a piece of code, and the optimizer will work out a good way of executing that time. But it has this balance of, it doesn't look for the best way to execute, it looks for a good way in a reasonable amount of time.
Okay.
And what's happening with this query is that we have an early termination in the optimization process, and the reason is timeout. And this is because we've hit this threshold of a reasonable amount of time. So what the optimizer's done is there are so many joins that it's done as much as it could to find a reasonable plan, and it's just going to take the best one in that time period.
Okay.
Does that make sense?
Yeah, absolutely.
So let's have a look at the next slide here, and we'll talk about why that happens. So this example here, we're doing a join between two tables. So we've got customer and orders, basically.
Okay.
So if we have a look, how many different ways can the optimizer choose to join these two tables? So it could choose to join customer to order, or it could choose to join order to customer.
Right.
So it's quite straightforward, and it'll be very quick to optimize a query that joins two tables.
Yep.
But the number of choices increases exponentially the more joins you have. So the order in which, just on that last bullet there, the order in which joins happen is important to the optimizer. In terms of the way that you write your code, it isn't important, because that's what the optimizer does. Incidentally, unless you start using hints in your code.
Right.
So there's a little tip there. If you start using query hints, the optimizer will assume you know what you're doing, and it will enforce the join order in the order that you've written it.
Put in the query.
Yeah, so,
Okay.
so that's when it becomes important. So if we have a look, instead of two tables, we'll move to three tables. So we're joining three tables. So if we have a look at the possible permutations here now, all of a sudden we've gone from 2 to 6.
Right. Okay.
So and the if we expand that even further onto the next slide, so the more tables that you join, the more possible permutations there are. So it's an n factorial possible permutations based on the number of tables in the statement. But what's really kind of starts to get quite shocking here is that you've got 10 tables joining together.
Wow.
And there's 3.6 million ways to join those tables together. And if you have a look at the next point, with 14 tables, 86 billion permutations.
So we're suddenly giving the optimizer a really big hill to climb to figure out what's the best way to do that.
Exactly. And if we move on to the next point here, so this is even before the optimizers had a chance to evaluate data access methods, which joins to do. This is just the join orders. So you're really, like you say, you're giving it a really tough job to do. And effectively what happens is the optimizer has to evaluate plans in a reasonable amount of time, as I've already mentioned. But we're timing out, basically. There's no point, if the best plan takes 10 days to find and the query takes 10 minutes to run,
right,
you're better off having a bad plan that finishes in 10 minutes.
Taking the time to find the best one.
Yeah, exactly.
Absolutely.
Exactly. So so what is happening in this situation is that the optimizer is timing out, and it's choosing the best plan that it's found in that time period.
Okay.
But what's interesting around the inconsistent performance, it's not that it runs slow, is that it will time out and use the plan that it had found. So its inconsistent performance in the same plan won't be guaranteed, and this is what was happening in that kind of scenario.
Okay. So we figured out the reason that we're getting inconsistent performance is the optimizer is scouring about trying to find a plan, and it sort of runs out of time to find the best plan. How can we help the optimizer then? Which I guess
so the key to it is when you find these tables, you've got 14 joins, is really to simplify the query first and foremost. And if you think about it in terms of 6 joins, you have 700 possible permutations, which is quite reasonable. And 7 joins has 5,000 permutations. So if you keep your table designed to 6 or 7 joins, that's a reasonable amount of permutations that SQL Server could run through in this kind of reasonable amount of time to come up with a good plan. And also consider the database design as well.
Okay.
So the solution in this kind of scenario, if we look at the simplifying the query, so what we did is to take this long query and break it down into multiple sections. If we just step through those slide builds, and ultimately we end up with a simplified query. Which we would then do multiple tables. We'd load them into temporary tables, which of course we talked about this morning. And then at that final step there,
select from that.
We would join those 3 tables together.
So interestingly, ultimately, even though we're doing the same query, ultimately we're getting the same data, it's more effective to take the overhead of having to create a temporary table and load some of the data we want into there, and then ultimately join against those multiple temporary tables than it is to try and get from the source table.
So we're breaking it down to give the optimizer a head start. So we've got 5 joins in the first query there, and the optimizer can do that relatively quickly, and everything else it can do relatively quickly, and then you just got to join them together at the end. So you're not giving it too much work to do in one single go.
All right, great example.
We see that all the time, so it's a real pro tip.
Fantastic. Any other pro tips you'd like to share?
Yeah, so I just wanted to wrap up this last session with a few kind of bullet points there that we didn't really have time to pack in kind of full sessions around these, but we see them in terms of a lot of performance tuning scenarios and mistakes that people will commonly make. And the first one is around variables and column names. So not having identical data types. We talked about data types earlier on in the first couple of modules. And if you take a data type of int, for example, int, small int, big int, so it stores the same values, but the range is slightly different. If you were to have a store procedure that took a parameter of age, for example, and you took that parameter and you knew it was going to be small, so you made the parameter a tiny int data type, okay? And based on that data, you took it in and you wrote that data into a table, but the age data type was int, for example. Okay. What happens is there is an implicit conversion from tiny int to int, which is a tiny, tiny CPU cycle change that you don't notice. But if you scale that out, again, we're talking massive concurrency, massive scale, what you'll find is that you've got a creeping CPU utilization problem because you've got thousands, 10,000, millions of implicit conversions between data types that look and function the same, but because they're not the same, there's a slight overhead there that causes a compound problem.
All right, okay. Good
so that's a really good one. So the other one here is avoiding the use of scalar UDF. So we talked about
user-defined functions, yeah.
Yeah, exactly. So if you use a UDF within a where clause, the optimizer has no idea of the data that's going to return to that function when it creates the plan. So it doesn't really know how to optimize the plan when you're using the scalar UDF.
Because it can't determine what the values are it's filtering on until it actually runs the function.
Exactly. So and again, it's a very, very common problem that we see. So show me this data where I'll tell you what I'm going to filter on later. How do you optimize that?
Yeah.
So what we would recommend is to run that scalar UDF and pass that value through as a parameter that the optimizer then has visibility of.
Okay.
So the next one is these massive decision trees in stored procedures. If this, do this, and then, or we have problems with dynamic SQL that's created in a massive stored procedure. If this, add this, and append this, and append this, and do this, because you end up with this scenario that we talked about before with parameter sniffing. Because the set of parameters used to generate the code that you've just created won't make for a reusable plan. So again, another common problem that we would see is this: people trying to do too much within a single piece of code. And as you've seen with the joins as well, you're much better off breaking it into smaller units to allow the optimizer to create separate plans for those code units.
And I mean, again, whenever I see a stored procedure that's creating dynamic SQL, immediately a flag goes up for me anyway. It's generally not the way that you want to be building your stored procedures. So that takes us to the end of the end. That's the end of the last module in this course. In this module, we've talked about SQL Server weights. We saw some really interesting things. We could see what are the tasks that are waiting on system resources or locks or whatever it might be. And then we talked about some tips for avoiding performance issues. So don't have queries that join too many tables. And we talked about the strategy of breaking those up into smaller queries and then joining them up at the end.
Exactly.
Which may seem counterintuitive because you're now running more queries, but each of those queries can be done much more quickly, and the optimizer can work with those. And then we saw some other performance tips at the end there that are hugely useful if you're trying to build a database that's going to perform well. So, as I said, that's the end of the course. So we have a number of things that we've covered in this course. We started with tables and views, and we talked about designing and implementing those. And other table-like structures. We talked about temporary tables and table variables, common table expressions, and partition tables was the other thing we spoke about there. We then moved on to talk about indexes, and what we were talking about there were our clustered indexes and non-clustered indexes that we would create on our tables. And we talked about how to maintain those indexes and update the statistics and deal with fragmentation issues within those indexes. We looked at stored procedures and functions. So how do we take code that we want to make repeatable to use again and again and encapsulate that in a stored procedure or a function and use that. We talked about transactions, and coupled with transactions, locking and isolations. And that's one of the real kind of nitty-gritties of how do you design a really good database, is to think about your transactions and the locking and how you're going to isolate different sessions, the concurrent sessions you've got from one another. We spoke about in-memory objects, and in particular the new technologies that appeared in SQL Server 2014, so memory-optimized tables and natively compiled stored procedures. And we talked in this final module about optimizing and troubleshooting queries. So we've covered a lot of ground. If you are preparing for the exam, the Developing Microsoft SQL Server Databases exam, what we've tried to do is to kind of pull out the really big areas that you should focus on. We haven't given you every piece of information you're ever going to need. So as I said at the beginning, don't assume you can watch this video and then go and sit the exam straight away. Use this as a kind of a way to look at the highlights of things that you should study for. Now, we are actually going to be working together on another course on designing SQL Server databases, which it maps to a different exam, but there is a certain amount of overlap. If you're going to develop things, it helps if you know how to design them. There's an implicit thing that makes things more intuitive if you understand the design principles. So I would recommend, even if you're only planning to do the developing exam, it's probably worth looking at the designing a data solution course as well, and get a feel for why things are designed the way they are and what are the considerations for designing an effective SQL Server solution. So whichever way you decide to prepare for it, I wish you luck with the exam. I hope you do well with that, and I wish you all the best luck and all the best use in the world of this information as you go and continue your career with SQL Server and manage databases and develop databases using the product. So thanks very much for your time. Christian, thank you very much for joining me today.
Thank you for having me, and I hope you found it useful, and good luck with the exam.
Thanks a lot, and we'll see you back on